Welcome, everyone. My name is Ron Bell. Morgan Sander Olaf, my co-organizer, and I are very pleased to welcome you to this first ever summit on drone geophysics. We believe that we have assembled an excellent program, providing you with a peek into the current state of the practice of geophysical science involving the use of unmanned aircraft systems, or as we call them, drones, for geophysical measurements. I wish to begin with, first of all, by thanking all of the speakers and presenters who have agreed to actually present in this event, as well as our sponsors. We have five. Lori, can you tell me the sponsors?
I sure can. We have great sponsors. We have Geometrics, Pegasus Airborne Systems, Hammer Missions, Drone Automation from A to Z, also Sequent and Southern Geoscience Consultants. Those are our sponsors, and they're greatly appreciated.
Thank you. I just didn't have it in front of me.
No problem.
We are actually, without much further ado, I am pleased at least to present, turn the mic over to Rick Miller, who is the past president of the SCG, to provide the welcoming comments to this event. Rick?
Okay, well, thanks, Ron. Morgan, appreciate it. Lori, thanks for the invite. Really great to see everybody signed on to the event. I think it's going to be a pretty amazing activity over the course of the next few days. And I really kind of wanted to spend a few minutes. I put together 3 or 4 or 5 slides to kind of talk a little bit about kind of where we are, where we were, and where we might go in the future. And I think that the entire applications of drones to geophysics really plays into where we see both professional societies as well as the community at large. Well, the direction that we're headed to, it's a very advanced direction, and it's one where we have a broad community base that will go along with us. And so I want to spend a few minutes right off this morning going through some thoughts on the summit and kind of where we are and where we want to go. And of course, now I put together some slides here, and this is just kind of to throw a little bit of historical stuff in here, as well as some futuristic looking things. And I'm used to giving technical talks, so over the last year as being SCG president, I've gotten more comfortable anyway with giving more informational talks and less in the world of technical. So I've thought I threw together a few slides here. And so the airborne geophysics, of course, has evolved dramatically over the last 100 years. First designed aircraft, of course, for geophysical surveys specifically was the Navy's P-2V reconnaissance plane. That's the one up there in the upper left. Now, the Japanese and US both used fluxgate magnetometers during World War II, but it wasn't until the early 40s probably before the P-2V came out, and it had a magnetometer stinger in the tail, it had an underbelly radar, and it had a gas chromatograph in the nose. It also deployed sonobuoys, both active and passive. And the mission of the plane was to search for submarines. So it was an overwater aircraft. It actually currently has the longest in-flight record without refueling of any aircraft to date. So it's even with the big super jets, it apparently has flown the longest distance. But anyway, that was a side note. As it evolved through its role in the Korean War, it then got into activities deploying passive seismometers in jungle areas, particularly during the Vietnam War. Now, the one reason I think that probably I brought this particular plane up, as you can see here, one of the passive seismometers deployed in the jungle, is my dad flew in this airplane as an electronics specialist. So back in the 50s, before I was even born, I had a tie to geophysics and didn't even know it. So this is kind of why I wanted to bring this one up. And as the other slides here show, the evolution of our airborne-based technologies from human-based into the unmanned scenarios have evolved to where we are in the world of drone now, and the drone world is expanding at a phenomenal rate. And then also I wanted to point out that these geophysical surveys were not the first remote sensing activities that took place. And back in the 1850s, actually, balloons and kites and even pigeons were deployed to capture aerial photos. And this is a photo here on the left, bottom left, of a pigeon. And you can see the camera actually has been attached to its body. I've seen some of the pictures from this, and it's amazing. You can see the pigeon's wings actually in some of the photographs. So that being said, I wanted to move a little bit into, okay, where we are today. Now, there's a lot of potential mobility and minimal access issues that come along with drone platforms. In other words, we don't have to worry about some of the economics and the feasibility of some of the problems associated with ground access. So that really opens up large opportunities out there, both from a safety perspective as well as opportunities for above ground reconnaissance. And the biggest drawback in the entire near surface geophysical applications has always been cost versus return on investment. There's no oil here to extract. You know, we think about our oil and gas colleagues, and when they go out doing geophysical surveys, they got a commodity thereafter. And so for us, even in cases for public safety, from a public safety perspective, you can't put a price on human life, but it's really hard to find a business model for sustainable application that equates to safety or verification and relate that back to a commodity with a defined value. And that's kind of been our big problem all along, is that a lot of times we find things people don't want to find, or we basically are looking for things that people don't want to look for. And so that makes our business models very challenging as we try to grow our opportunities. And there are so many opportunities out there. I wanted to switch a little bit now, look at SCG in terms of this as an example of a professional society. And I know that the group of people that have been gathered here for this particular webinar, this summit, has a broad background in different professional geophysical or different societies in general. But I think for most cases, we all kind of converge and coagulate around a certain set of forward-looking strategies. And I think the one thing that SCG in our strategy, basically, as we developed in 2020, we actually refreshed it in 2020, is a consistency and a diversification, not only in revenue streams and our presence around the globe, but also in members, not only member diversification, but also offerings beyond that oil and gas core that we've always had. And this drone summit is exactly the kind of program that fits in the long-term interests of SCG for sure, but almost all societies. This clearly is an area of great potential for growing our profession and helping to support our professionals, our geophysicists. And along the same lines, SCG is initiating a new program in geophysical sustainability, which is consistent with our strategic plan. It also aligns with the UN Sustainable Development Goals. And the reason I bring it up to this community, because so much of what's in the UN Sustainable Development Goals and also the geophysical sustainable goals relates back to this community. The design here is to increase awareness of how applications of geophysics can and contributes to the economy, the society, and protecting the environment. It clearly demonstrates how significant geophysics is and can be to the long-term occupation of the Earth. So I think that, this being said, this is a new initiative. It's global. It's involved not only SCG, but SPE and several other societies are also getting on the same bandwagon associated with the National Sustainable Development Goals. But this plays right into where we live, the near surface and our applications of geophysics. So it's very exciting going forward. I think the potential is quite significant for not only drone geophysics, but all near surface geophysics. So basically, finally, I just wanted to again, welcome everyone to the first, what I hope will be a recurring event, if for no other reason that advancements in this science are coming so fast and the impact has such potential and such great long-term application opportunities, and problems that have been beyond our capacity are now within striking distance, and even more become feasible as the technology evolves. So thanks to the organizers, Ron Bell, Morgan Sander Olaf, along with Lori Wetzel, for bringing this outstanding program to the community. And I wanted to say that SCG and the Near Surface Technical Section are very pleased to be able to host the event and look forward to a really great several days of engagements and conversation. So with that, I'll turn it back over to Ron. Ron, I look forward to a great conference.
When I have to get used to this muting and unmuting business, but thank you very much, Rick. That was a great way to start off our event here, our workshop. Before we get into the first talk, let me just say a few words about what we are looking at for the future after this event. That is, we're working with the Near Surface and the SCG to put on a second summit on drone geophysics. which we hope to do in the fall of 2021. And we're looking for people who, who would be interested in joining us on the organizing committee. If you're interested, contact Morgan or myself or Lori. And then in the fall of 2022, we would like to expand it to be more than just about geophysics. We see that there's a very significant synergy between geophysics and what is traditionally called remote sensing. There's an exciting number of sensors being developed that could be very much integrated with what we're measuring in terms of geophysical data. The lineup we have today, I think I'll get into it. Is Jan on the line now? Is Jan Frankie?
Yep.
Has he showed up?
Yeah, I'm right here.
All right. Jan, I'll first apologize by saying I don't have your abstract in front of me. I don't have your bio, so I'm going to let you do your introduction on your bio for you. Jan's talk is UAV Geophysical Sensor Roadmap 2020. He actually was gracious enough to actually write an article for the Fast Times in the drones and remote sensing issue that recently came out, and I found it fascinating, and I hope you all will not only listen to his talk but get the article and engage with Jan. Jan, I'm going to turn it over to you.
Great. All right. Hopefully everybody can see my screen.
Yes.
All right. Good morning, good afternoon, good evening, wherever you guys are. I guess if you're in Australia, sorry about that. My name is indeed Jan Franke, and I'm based here in Vancouver, Canada. I've been working with long-range ground-penetrating radar for the last 30 years, and over that time, I've had the opportunity to work in over 100 countries. In the last few years, I've seen this dramatic increase in interest for mounting radars and other geophysical sensors on drones. Over the last year, AMIRA, which is the Global Mining Industry Research Organization, assembled a team of world experts in specific geophysical instruments to map out the future of drone geophysics. The project itself was sponsored by, I think, 18 of the largest mining companies in the world, and had representatives from Boeing and other large UAV stakeholders on board. The goal of the project was to define the next steps in instrumentation research, both from a geophysical standpoint as well as the UAV standpoint, to drive the use of drones in geophysics and particularly mineral exploration forward for the next 5 to 10 years. So the specific methods we focused on were magnetics, electromagnetics, radiometrics, hyperspectral imaging, gravimetry, and of course, GPR. We also reviewed this current state of affairs and state of the art in UAV technology itself. Perhaps most importantly, though, we looked at the legal landscape for the use of surveying drones internationally. Now, there are a number of other methods that we also looked at, including seismic and green LiDAR for bathymetry surveys. But today I'm going to try and focus on the main techniques that I mentioned. So, drone geophysics, perhaps a decade ago, or even 5 years ago, that term would definitely raise eyebrows. And certainly the idea is not new itself, right? Like people like Tony Barringer in Toronto were thinking about placing magnetometers on unmanned aircraft in the late 1970s. In the case of magnetometers, which are, generally small and portable, what held back drone geophysics was the drones themselves. In the 1990s and 2000s, drones to us were kind of the purview of Hollywood movies or the military. And then sometime around, I guess like a dozen years ago, hobbyists came up with the first quadcopters and ArduPilot. An industry sprang up around what was initially considered, I guess, toys for geeky adults, right? And rather than just spying on your neighbor's pool, commercial applications grew to include aerial photography. And around the same time, photogrammetry software packages were being adapted to make 3D models from these drone photographs. And this led to the use of drones for real estate advertising, accident scene reconstruction, and in mining, mapping stockpiles and bench advancements in open pit mines. So as cameras became smaller and other types of cameras like, I guess, thermal and hyperspectral were being carried on smaller and smaller drones, it wasn't long before the first cesium magnetometers were being long lined from a UAV. I think that was originally by a German company I saw about a dozen years ago. And then, of course, Geomatrix and GEM Systems released a more robust mag sensor, and the rest is history. So as we can see from this graph, the commercial drone industry worldwide is apparently poised for exponential growth over the next few years. And there's no doubt that geophysical surveying from drones will follow. So why is this now? Why is it all happening now? What's this great excitement? Well, as I mentioned, drones, like the internet or many other technologies, have gone from being the domain of the military to hobbyists, to a consumer product, to being its own industry, right? And much of this is due to, well, better batteries and the emergence of like mass market drone manufacturers like DJI. This has coincided with a move away from monopolies in geophysical instrumentation who have traditionally dominated the market. Right? Geophysical tools are now made in people's backyards, and they are outperforming instruments made kind of by the big players. And at the same time, instruments are being developed globally. It wasn't long ago in my career, maybe 20 years ago, that almost any geophysical tool was made in one of three places. It was either here in Canada, in the States, or in Sweden, and that's about it, right? There were a few other instruments, but mainly those three countries. And now we see amazing instruments coming from the Czech Republic and China and Belarus and all sorts of strange places, which haven't traditionally been producing geophysical equipment. But what else has happened? There's been a massive improvement in electronic components and a huge decrease in prototyping costs. Whereas, a few years ago, it would have cost me tens of thousands of dollars to prototype a new type of radar. With 3D printing and rapid PCB prototyping, I can probably knock one off for a couple $1,000s now. So it's a lot easier to make instrumentation. And finally, and this is really important, all the other ancillary sensors are benefiting from advancements in unrelated sectors, right? For example, there's a massive need for lane-aware positioning for automated driving. So not just normal GPS, but knowing which lane the car is in and where within that lane, all within very difficult urban canyons. And this has led to the development of very low cost, yet high accuracy L1, L2 chips, which are at centimeter precision, right? Now, such technology, geez, a few years ago was tens of thousands of dollars for an RTK L1, L2 chip. And now they're worth a few $100s and fit in, on the tip of my thumb. That's amazing. Heck, entire computers with massive memories and hard drives are now fitting in my hand and cost a couple $100. So those are huge drivers, all those ancillary sensors. So for drone geophysics to really take off, what do we need? Well, it's not just about making a sensor small and slapping it on a drone. The drone needs to be able to carry it for a long flight. And since most sensors need to be close to the ground for the best data, the drone needs to follow the terrain and avoid running into trees or cows or people. The sensors themselves need to be sufficiently small and light without losing too much accuracy. And most of all, the sensors need to be at a reasonable cost. The legal situation is very complex and very dynamic. What is legal today may not be legal tomorrow, and certainly varies dramatically from country to country. This is particularly important when we consider mineral exploration project for drones, where the aircraft will most certainly be outside of the pilot's range of sight. And finally, and perhaps this is the most important question, just because we can place a sensor on a drone doesn't mean we always should. The use of drones needs to solve a problem for the industry, be it being more safe, or tighter station spacing, collecting different offsets at once, complex source receiver geometries, etc. Just because we can doesn't mean we always should. So let's consider the different deployment methods for geophysical sensors on a drone. As is done right now, we could simply mount a sensor on a rotary or a fixed wing drone directly. In the case of magnetics or EM sensors, or arguably, I guess, even GPR, this might mean that the sensor needs to be tethered, ideally from a rigid tether, some distance away from the drone's EM field itself. Okay, but that's doable. To be truly effective in geophysics, though, the drone itself should be relatively inexpensive and have good endurance, so it needs to be lightweight. But that's just one UAV. Let's think out of the box. What if we employed more than one drone and more than one sensor, right? For example, a swarm could create a transmitter, a larger transmitter dipole moment for an EM, for example, or even a GPR, and enable complex source receiver geometries, or concurrently serving horizontal and vertical gradients for potential fields. In almost all cases of geophysics, having that sensor as close as practically possible to the ground yields, of course, the best data. In some cases, the sensor may need actual ground coupling. So it is, if it's really sensitive to rotational or vibrational noise or kinematic noise, in the case of gravimetry, when we'll get to that, the gravimeter needs to be on the ground. So in these cases, a deployment method might be to actually land the drone at a predefined location. And perhaps in the future, AI and computer vision can be used to find suitable landing spots all within an allowed radius. And finally, this could be multiplied so that a fleet of drones are landing and taking off, picking up sensors at set grid points to speed up data acquisition with multiple sensors. So let's go through the different methods that we looked at in our study for the last year. And we're going to start with the most common drone method, magnetometry. And this is certainly the grandfather of drone geophysics and early systems we used in unmanned aircraft dating back to the 70s. So today there are dozens of suppliers of pretty small, lightweight, total field sensors consisting of a few $1,000s. That's what they cost. Most of the ones designed for UAVs work on cesium, or I guess potassium vapor mags, as well as some tiny atomic magnetometers. And you can deploy two of these sensors in gradiometry measurements, which is obviously useful for separating the effects of shallow and deep sources. So that all sounds wonderful, but as with any geophysics, there's always catches. Reducing the interference from the drone itself is of utmost importance, and there are some well-established methods now to address these issues, such as long lining the sensor from a stiff cable, or reducing the amount of metals in the drone and using shielded cabling. All of that stuff's pretty well studied now. Of course, to maximize the effectiveness of a drone survey, the goal would be to fly as close to the ground as possible. And there are operators now, certainly in Australia, who now initially fly a drone photogrammetry mission to generate a very accurate DEM, which they then use to accurately follow the terrain itself with the magnetometer drone. And perhaps with better terrain sensing sensors, low-level flights can be done autonomously without having to fly the site initially. So since drone magnetometry is somewhat fairly mature now, there are probably not going to be significant drops in sensor costs, we don't feel, simply because there are precision instruments which require a lot of manual labor to manufacture. We do see the potential of compact full gradient tensor systems, but perhaps the most useful improvement, if it gets to this, may come from the use of coordinated swarms, or at least multiple drones at different elevations for gradiometry measurements. And this can be done, of course, right now with multiple passes of a single drone, but that would require a really careful base station calibration. So that's where we are with magnetometry. Let's skip over to the EM surveying space. Now, remember, this study that we concluded over the last year was done primarily for mineral exploration, not near surface geophysics. And right now, there aren't any existing deep EM systems suitable for mineral exploration on the market that we know of. But there's certainly a couple of repurposed ground frequency and time domain EM systems, which are being stripped down for drone use. There are, VLF receivers have been placed on drones since the 1990s. So there's nothing hugely new there in terms of research space. But okay, so there's some solutions for near surface conductivity and metal detection with these repurposed EM systems. The real challenge of going deeper is, of course, for mineral exploration. And the challenge there is that you need a very high dipole moment, which means a large transmitter, a lot of power. So that means generators and massive transmitter loops, which are just not going to fit on any drones that we know of right now, other than making a Cessna a drone, essentially, which would ameliorate the whole point of having a drone. So they're too large. The transmitter is going to be too large to lift on even by the largest drones. And the next problem is, if you could lift the receivers, the whole gimbaling system for an EM system would need to be really, really sophisticated to compensate for the rotational vibrations and any rotational vibrations that would induce a huge amount of noise on a vector dB/dt sensor. And of course, well, EM, MT, IP ground sensors are pretty low signal to noise ratios when operated in the air in the first place. So how can a deep EM system be used with a drone? Well, we determined that carrying the actual generator and transmitter by a drone is just not feasible. And perhaps the most promising idea that we came up with, and it's been done before, and actually I think there's an ExxonMobil patent on this, is to use a conventional helicopter transmitter loop coupled with a high density of very low cost EM sensors, which are then mounted on drones and landed at specific grid locations in like a grasshopper mode. So you'd have this whole array of small, lightweight EM sensors on a grid that the grasshopper would pick it up, move it over, and drop it in a new grid location with an overflying transmitter. And of course, the grasshopper array then permits both a magnetic and electric second order effect airborne IP measurements, theoretically increasing the low frequency signal to noise and the detectability of the IP targets with economic grain sizes, in theory. Let's look at hyperspectral imaging. Historically, these sensors have been placed on satellites with 40-meter pixel size, and over the last decades, they've been moving to being aircraft mounted. Now, there are currently, to the best of our knowledge, I think 18 manufacturers of 8 hyperspectral sensors, but many of these are used for agricultural and other applications. For mineral exploration, you really need the visual and near infrared and shortwave infrared ranges, and there are only 4 manufacturers that we know of currently making units which could be mounted on a drone for mineral exploration purposes. The massive drawback here for hyperspectral scanning is the cost of these units. These things are $300,000. And I don't know many users that are willing to place these on a drone, which might experience a flyaway or landing into a puddle. So we're unlikely to see the sensors themselves lowering costs due to the precision engineering that goes into making them. And there's just not a lot of market demand. So the manufacturers don't see them coming down in cost dramatically. And of course, the point is to get as close as you can to the rock outcrops or in quarry walls, right? And if you're doing that, then it requires some very careful control or autonomous flight using very accurate terrain models. And then the technique to process off nadir imaging hasn't been really well developed either. So regardless of the costs and complications, there are some interesting possible applications, such as imaging rock chips from dust piles from blast holes in an open pit bench. So as you're blasting ahead your bench, you're drilling a grid of blast holes. The rock chips are usually sitting in a little pile. Flying a drone with a hyperspectral sensor over them could be used to map in real time grade control, right? Or even control the blast planning itself. Similarly, monitoring stockpiles for grade control is an obvious application. And for environmental monitoring, tailing storage facilities and streams could be mapped theoretically for acid mine drainage. And even in heavily vegetated areas, you could use a hyperspectral sensor on a drone to image rock outcrops, which would, maybe precision flying a drone over small exposures between trees or looking at dry stream beds. So there are applications. Shift over to gravimeters. Now, I've heard that there are some stripped down land gravimeters from Syntrex that have been used in grasshopper modes, I think in China, where the drone lands the instrument at a predefined point and the reading is taken. However, there are some very new and very small, relatively light MEMS sensors which are being developed right now. MEMS is micro electrical mechanical system. So it's basically like taking a device and using nanofabrication to miniaturize it, right? And they can get these systems down to a couple kilos. The big problem, though, putting any gravimeter, regardless of its size, on a drone is the kinematic isolation. So even with the fastest and most accurate RTK receivers, they're just not going to be sufficiently accurate and precise to track and compensate for the flight dynamic variations and that kinematic vibrations. Let alone, the vibration of the drone itself. The gimbaling system would certainly be larger than the gravimeter, so that becomes now impractically large. And so we felt the only practical solution may be, again, that grasshopper mode of acquisition, whereby the drone lands the gravimeter at a predefined location, the gravimeter collects its data and, it self-levels, ideally within a few hundred arc seconds, and then the drone picks it up and takes off and does it in another location. The problem, though, is that all of these new MEMS gravimeters just don't have the ability right now to produce the resolution required for geotechnical or mineral exploration work. They might be of use for petroleum exploration and military applications, but not right now for mineral exploration. And then in radiometrics, there's a large number of commercial sodium iodide, cesium iodide, and bismuth germinate crystal detectors, which weigh, well, we've seen them as small as 1 kilogram and up to 100 kilograms. And there's been 3 of these detectors, I think ranging in like 20 to 145 kilograms, which have been tested on massive drones for mineral exploration applications. Now, to make radiometrics a more accepted method in mineral exploration, the detectors themselves need to be as small as possible while maintaining adequate signal-to-noise ratios, which is always going to be a compromise, right? There's new thallium-activated cesium iodide, which looks very promising, and they're supposedly one of the brightest scintillometers known. And this means that a crystal size might be smaller and thus lighter and liftable by a drone. So our study concluded that perhaps a 4-liter detector would be required for radio element mapping for mineral exploration. Yeah, 4 liters. We also concluded that the radiometrics, it would be, the most uptake by the mineral exploration industry if a lightweight drone, a lightweight system, so let's say 4 liters, which might be a couple kilos, could be developed to be flown in concert with another geophysical sensor. Otherwise, doing it from the ground or from a low-flying aircraft might be just as cost-effective. Finally, let's talk about GPR, my favorite subject. So, look, the idea of hanging a GPR from a helicopter has been around since the 1980s, particularly for glaciology studies. The dielectric changes between the air and ice isn't much, and most of the energy goes into the ground. So you get, very high resolution imaging kilometers in depth. There is nothing special there. That's super easy. But as we move away from ice, things get a lot trickier in terms of physics, and in some cases, the law. And this is something that won't be discussed today, but I need to raise it. The issue that is that in Europe and here in Canada and the United States and potentially other countries, it is illegal to operate most radars over 1 meter above the ground surface. That's it. It's against the law. In Canada, it's the RSS 220 rules. If you're wondering why, well, it's because the FCC rules, when they were drafted, it was kind of feared that GPR could leak EM energy and interfere into other radio signals and protocols if operated in sensitive areas like an airport. And the fact is, of course, that the average power emitted is far less than your mobile phone probably, but those are the rules. Well, this 1 meter rule actually kind of bodes well for the physics as well. You see, once you're more than about 1 wavelength above the ground, you're no longer ground coupled, and the physical size of your antenna should increase significantly in size to maintain that same frequency. Now, there are clever antenna designs which you can use to reduce that effect, but they're not very aerodynamic, and there's no way you'd be able to carry that from a drone. So on top of that, all of that problem is the Fresnel zone, which is this, the illumination zone of the antenna, and it becomes very wide when you're in the air. So now you've got a problem of side lobe problems where you're picking up absolutely everything. You start seeing massive effects from any above ground object, be it trees or buildings, really anything, which you then need to identify and ignore when you're interpreting the data. But perhaps the biggest problem is the reflectivity of the ground itself. In wet conditions, particularly, you're losing up to 60 to 80% of your energy at that ground level. And no amount of cool antenna design or physics is going to change that. That is just physics. And again, these are only relevant if you're, more than, say, 1 wavelength off the ground, decoupled from the ground, and you're using maybe traditional electric field antennas like a dipole or a bow tie. Yeah, we've seen amazing data, and we will see amazing data, no doubt, from bathymetry surveys, but there's a catch there too. Even a small increase in total dissolved solids, so that is a small increase in conductivity, which doesn't take much in fresh water, dramatically limits the penetration of radar. Knowing that as little as 20% of the energy is actually getting through the water column, radar is going to work best in as close to pure water as possible. As an example, I just wrote this on LinkedIn yesterday, we developed a 40 megahertz dipole radar system for use in an automatic clothesline system about 1 meter off rivers in China and India for flood control applications. This is an automated system that would shuttle itself back and forth and measure the base of the river. In China, these rivers were glacial fed, and we got 8 meters of penetration, absolutely beautiful data. You take it to India, 0 meters of penetration, and that's simply due to the TDS caused by the sediment load and agricultural runoff. So simply be aware that the use of drone for GPR is highly site specific, and certainly more so than for ground GPR. So with all these caveats, what are the applications for drone GPR? Well, as it turns out, there's quite a few, and many of them are somewhat strange. We've been getting almost weekly requests to build custom drone systems for really strange applications. As of this month, we're working on it with a major European rail network to develop a ballast mapping radar to use on their high-speed rail systems, which, you know, they've been doing GPR for decades, but having an innocuous drone doing the same work will you know, to rapidly assess the track conditions while keeping the lines open is much safer. An insurance company in the US, which specializes in farms, wants to use a forward-facing GPR on a drone to scan concrete silos for cracks to assess their stability for liability issues. There's a hydroelectric power company in Russia that needs a drone-based radar to map snow depth and snow moisture, because for them, the snow is their resource every winter. So the list goes on. So look, there's a few drone radars on the market right now. Some are larger, some are smaller. But all of that is, you know, they're all useful in the upper few meters. But since antenna size is inversely proportional to penetration, it's to frequency. So to get, say, a 20 megahertz drone in the air for deep penetration is just completely impractical. Or maybe not. There's new antennas that are magnetic antennas that are only 20 and 30 centimeters long, and they can be as centered as low as 10 megahertz. And since there's no magnetic contrast between the air and the ground, usually, the ground coupling isn't a big issue. So if you have, for example, a series of small, low-cost, low-frequency radars, then the next step might be to deploy a swarm of drones to carry multiple transmitters and multiple receivers for multifold acquisition. And this could be used for moisture mapping, or by taking the ratio of the magnetic field to the electric field, you should be able to get shallow EM conductivity along with your low frequency radar. So there's some very interesting concepts of, you know, fancy source receiver geometries, which are now possible with GPR on drones. So folks, that's it. Thank you very much for your time and your attention. I think we'll be taking some questions now.
Yeah, thank you, Jan. There's a couple questions on the chat part of this presentation. Can you see those questions?
Yep, I'll bring them up right now.
The one that's out there is, please describe the grasshopper mode. This person is unfamiliar with it.
Okay, so this has not been, I can't see the chat right now, but this has not been well established. But the concept of the grasshopper mode is simply that it's for sensors that require ground contact, be it because of literally ground contact, or in the case of a sensor that is so sensitive to vibration or rotational noise, needs to be on the ground in a calm setting. So the idea is that a drone would be attached to the sensor, would lift the sensor up, carry it to a pre-designed or pre-designated location, and then lower it and land at a pre-designated location that has good ground contact. The sensor would, perhaps in this case of gravimetry, level itself and set itself as close to upright as possible. The reading would be taken, and then the drone would pick it up and take it to the next location, and potentially doing that with a whole fleet of drones at the same time.
Thank you. The next question, have you seen application of drone geophysics for landmine detection?
Yes, of course. So obviously that's been a huge push in the last, even 20 years. And there are Japanese universities that have been pushing the use of very clever array radar sensors, for example, coupled with magnetometers on low-flying drones. Tohoku University, I think, is one of them. So there's been a lot of there's a lot of funding, obviously, towards that. And I know that we'll be hearing from our friends from Latvia, and I believe they've sold some 501 gigahertz antennas looking at anti-tank mines, which tend to be obviously larger targets. So yeah, it's being done, and it's being done as well.
Okay. I guess this person has heard about different groups combining the MAG and the GPR together, specifically for landmine detection. Have you heard of that?
Yes, exactly. No, that's exactly right. So that has been done. And you can do that with two sensors that don't interfere with each other, right? The MAG itself is reasonably passive. The problem, though, is when combining a GPR with a MAG, the GPR is emitting an electromagnetic field. So there are some noise components that need to be ameliorated with the magnetics. So yes, you can put them theoretically together, but you have to be very careful with your with the pulse shape of the GPR, because you are creating as part of that, you're exciting the electric field, which then creates a magnetic field. So you are creating a magnetic field, which may be picked up by the magnetometer if it's not sufficiently shielded or removed.
All right. Jan, thank you very much. We're run out of time. If anybody has a question, we have a chats, as I understand it, we have a chat thing. Lori, can you kind of elucidate on that a little bit?
They should only put their questions in the question and answer box. Anything that's not answered immediately will be answered afterwards. So I'm going to grab those questions and put them in a document.
Okay, which kind of brings me to the point that after we have our morning presentation, we're going to have a discussion and summary, and then there'll be a networking room where we can actually talk about a lot of different topics and ask questions. So I'm going to turn the floor over to Morgan, who's going to introduce the next speaker.
Hello. So our next speaker is Elizabeth Berini. I'm sorry, Elizabeth, if I pronounced your last name wrong. Her presentation is on UAV geophysics, safer, faster, and cheaper. She is affiliated with Sequent. And with that, Elizabeth, are you ready?
Yes, I am. I am going to share my screen, I guess, now. Allow me to do this. Okay. All right. You do see my screen, correct? And I'm clear?
No, I don't think we can see it yet.
Nope. We see you, but not your shared screen.
Okay. Sorry. I thought I had the right screen here that I'm sharing.
All right, it looks like you are sharing your screen. It's just taking a minute to load.
Let me know.
There it is. Mm-hmm. Wonderful.
Thank you. Thank you. We have a great set of talks lined up, and I'm looking forward to all of them. I will be echoing a bit of what Jan so eloquently covered, but at a kind of a higher level. The annual drone sector revenue at large in 2018 exceeded $1 billion US. And it is projected that by 2021, about 400,000 commercial drone systems will be sold. The trend carries to drone geophysics, which is an evolving and exciting area with great potential, and it is quite multidisciplinary. The title of our presentation is Faster, Safer, Cheaper, and intends to imply the direction we are aiming towards. It is important to move in this direction because that's what will firmly establish drone geophysics in exploration. I will keep the history of drone surveying very, very brief because it has very well been covered. Then I'll talk about where we are in the applied world and what is kind of lurking on the horizon. Drones, of course, initially were used by the military, and then they were adopted in different sectors. In the civil sector, they were used for monitoring cables, pipelines, infrastructure, ground stability, using photogrammetry, multispectral, and LiDAR data. And in agriculture and forestry management, primarily for monitoring soil moisture and the health of the crop and the vegetation. The interesting one is also that in archaeology, there is an international initiative with various degrees of success to cover sites with LiDAR, like the entire globe, wherever we have archaeological surface sites, for the preservation of the current state of the archaeology, because these sites are disappearing fast and at an alarming rate, being it due to environmental factors or altered by human activity. So geophysics, actually, maybe I should go back. I missed one point there. About 10 years ago, UAV surveys appear on the geophysical exploration scene. Of course, it started with mapping of the terrain and the geology, but the very first instrument, as we know, was magnetometers. The reason being that magnetometers are small and robust, and magnetic survey data is a good investigative tool in geophysics. Magnetic drone surveys also acted as a very solid proof of concept, and drones gained a fast acceptance in our exploration field. Then we started seeing all these other sensors that Jan kind of comprehensively covered to be adapted to drone surveying. Also, to note and go back to the previous statement that I made is that that drone surveys in exploration only account for a very small fraction of the wider drone applications. And it is an attractive, very attractive proposition in geophysical exploration with key advantages. It's attractive because it offers the best of two worlds. Being low to the ground, you get a much improved precision, while being off the ground offers a safe access to very rugged topography. Then being much less involved than airborne manned surveys in equipment, staffing, deployment, drone surveys are cheaper to conduct, faster to deploy, and in that respect, they have an upper hand on conventional manned surveys. Along with the higher precision, since multi-rotor drones can hover and move vertically, we can plan and achieve a very close autonomous drape. Of course, relative to manned surveys, the rate of data collection with drones is slower and limited to fewer sensors, but the gain in resolution outweighs what airborne surveys offer. There are also hurdles that cannot be overlooked. The old age issue of the disconnect along the entire exploration stream being one of them. Drone geophysics is still an evolving method, so it is absolutely crucial that the different stakeholders maintain open lines of communication and collaboration. Research is being conducted at all fronts. On the hardware front, encouraging progress is constantly made in increasing the speed and the payload of the drones. In the meantime, geophysical sensors are miniaturized, and academic research is focused on interpreting the drone collected data. As for the methodology, the approach of how to conduct and process drone surveys is totally different from both ground and airborne surveys and has its challenges and considerations. Standards are developing and must adapt to regulations such as the line of sight requirement, but the regulations are not standard globally either. A lot of things are still in flux. In time, regulation will stabilize towards more practical convention. And all of this kind of goes hand in hand. As the hardware technology improves, we see better accuracy and smaller sampling rates. The sensors are producing progressively larger volumes of data, and in fact, probably well oversampled data. We also need to figure out some practical guidance and dial back from what sensors are capable to what makes more sense. That said, a continuous concerted effort in close collaboration of the scientific community, the researchers, hardware and software manufacturers, along with the validation in the field is absolutely crucial. So where are we today? Initially, geophysical drone surveys were conducted in small areas for purposes such as locating drill caps or some other localized target. So they were intended to fill the gap between airborne and ground surveys. The trend, however, leans towards displacing airborne surveys in exploration. But in order to get there, we have to solve the issue of covering large survey areas with short flight spans in a practical fashion. How to easily and effectively and efficiently break down the survey area into individual flights and then assemble them smoothly and easily back into one coherent data set will be when drone geophysical surveys will be totally embraced by all sectors of exploration. As for the benefits, surveying lower to the ground is an attractive proposition. And this illustration on the bottom right aims to make the point visually. This is a relatively flat area of about 1.5 by 2.5 kilometers and was provided by Ron Bell to us. It is shown as if it was surveyed at about 150, it's MAG data, 150 meter terrain clearance. Of course, not much structure emerges. If we move it down to about 100 meter terrain clearance, the resolution improves, but if you go further down to about 30 meters, so much more emerges. The approach of conducting drone surveys must also be adapted to the limitation of the drone survey, from the planning stage to execution and processing. Overall, contractors spend still a disproportionately large amount of time in the field conducting drone surveys. Let's break it down into the individual steps. Currently, drone survey planning takes mostly place in the field. Subject to the terrain and line of sight and flight duration, the area is broken down into this mosaic pattern with some overlap, and then as the survey is executed, the plan is adjusted and changed multiple times, and it consumes far too much time at the moment. As such, when it comes to the execution, generally, we end up with a lot of redundant coverage. It would be by far preferable to avoid or at least minimize redundant data collection. By the way, too much time spent in the field, of course, directly translate to higher cost of the project. Since continuous lines cannot be flown and the area is broken down into a mosaic pattern, the leveling, merging of the data could also be painstakingly complicated. And ultimately, to conduct the interpretation and analysis stage, you need this one coherent data set, leveled data set, which should not be cumbersome to produce. Let's look at these individual steps. As you know, drone surveys cannot be executed the same way as geophysical airborne surveys. To adapt the survey plan for drones, we need to take into consideration the defining factors, which consist of the visual line of sight, proximity to ground, the short span flights, and where the accessible and good locations for the takeoff points are. And then break down the survey area into sub areas in a mosaic pattern with lateral overlap, the size of each sub area being limited to the length of the flight, which varies, of course, from system to system. Using software tools, and we can easily and quickly produce an optimal pattern on site. In the execution stage, the design of the survey must be easy and quick to modify and adapt. once in the field, the intent is to conduct the survey in the shortest possible time without compromising quality and coverage. Inevitably, subareas will be modified to better fit the terrain with a maximum line of sight coverage. And when working out, the reflight redundant coverage should be avoided. These steps need not be painstakingly complicated. The use of software tools to optimize the reflight in consideration of all the parameters and regulations would expedite, of course, the process. We may need to change in the field the subareas or move the takeoff points for a better coverage and adjust as we go. Then create the flight path and conduct the flights. Ultimately, we should also be able to conduct the data QC and correction and merge and level the data all while the survey is in progress. When it comes to the processing stage, it only makes sense to automate the repetitive tasks, as there will be as many repetitions of the entire process as there are subareas. The merging of the flights should be streamlined and the leveling adapted to the mosaic survey pattern. Of course, the standard corrections and data integration process should be customized to the mosaic pattern. Now, these are just the same steps going quickly through. All of these can be automated, optimized, so that the hurdles are removed of what we are encountering now with airborne surveys. Improving and automating the process simply will translate to a better, faster turnaround, and thus a cheaper process, cheaper project.
3 minutes, Elizabeth.
Yes, I'm speeding up, sorry. So the ideal process and interpretation workflow would consist of minimizing the time consumed in the field in each one of these steps, automate repetitive tasks, adapt the data processing workflow to the survey pattern, easily integrate other data types such as LiDAR, geology, and what you have, and a close collaboration and good communication between the research entities, the people conducting the survey in the field, and the software solution developers is absolutely key. As the sensors are being made smaller and other methods are coming online. Again, Jan covered very well these aspects. The top few are already used in the field, but the ones that are more effective or at the moment kind of need a grasshopper mode, they are further in the future in terms of coming online. So what do we expect to, as we go forward, workflows to standardize, more geophysical methods to become available, commercially available. And this is important because we need a panoply of data types to choose from, subject to the type of the exploration conducted and what the intent is. Alongside of the above, the software will evolve to overcome the hurdles, speed up processing, optimize data volumes, and essentially help the geoscientist focus on the interpretation. So in conclusion, geophysical drone surveys will continue to become faster, safer, and cheaper. They will displace conventional geophysical survey methods, and they will also expand gradually into other domains. And this summit is a proof of the fast evolution in drone surveying. I'm almost there. We would not have been able to identify these problem areas on the drone workflow journey without the close collaboration and support of Ron and Kiavash Parvar. And this is the end of my presentation. Thank you for your attention, and I hope that I didn't go over time.
Thank you, Elizabeth. We appreciate your presentation. We have a handful of questions, but we kind of ran into our time. So what I would like to suggest is that maybe you can go into the question and answer portion and answer them. We're going to take a short break now for 10 minutes so everyone can either grab coffee or tea, whatever is your preference, and then we will begin again at 10:10. We will also have time to kind of continue this discussion and answer some of the questions that haven't been gotten to during the discussion towards the end. So if there's anything that you'd like to ask that hasn't been discussed yet, there will be more time. So don't worry.
The next speaker is Jana Gustafsson. Did I say that correctly? With Guideline Geo. Title of her presentation is UAV-based GPR and near-surface geological mapping.
Okay, let's see if I can share my screen. Can you see it?
Yes.
Perfect. Let's see. Okay, so let's talk about GPR, drones, and geological mapping. This paper was written together with my colleagues, Jesper, Johan, Morgan, Andreas, and we are all from Guideline Geo. The presentation will comprise of 3 parts. The first one is a short background and aim, and then I will give an explanation of the HDR technique, measurements and results, and finally part 3 with some conclusions. During the last few years, we have seen a dramatic increase in the use of unmanned, sorry, I can't see my, 1 minute. Like that, yes. I have to see what I'm doing as well. Okay, let's continue. Yes, during the last few years, we have seen a dramatic increase in the use of unmanned aerial vehicles for collecting geophysical data. As we all heard, much of this development has been driven by the increase in the capacity of these platforms. Longer flight times and increased payload capacity have made it possible to use a wider range of geophysical sensors. Being able to deploy GPR systems from a UAV is especially interesting since it facilitates measurement in dangerous or otherwise inaccessible areas. But most application and investigation made so far has considered measurements over lakes and rivers. But during testing of equipment we have developed, it became apparent that this drone-based GPR was in no way limited to bathymetry only. So we wanted to see how well in-air measurements works for other applications as well. So other interesting applications for drone-based GPR can, for instance, be mapping of soil layers, mapping of peat layers, and of course looking at both snow and ice. In this paper we have looked at all these 3 different types of applications. One key for good GPR measurement is of course the antenna technique. So for the drone-based GPR we have used a HDR technique, which stands for high dynamic range. This HDR technique gives a really fast antenna due to the real-time sampling of the traces. And this again means that we can stack more data and by that increase the signal to noise ratio. The HDR technique also gives us a better bandwidth and by that higher resolution and a better depth penetration. So if we look at the real-time sampling technique in more detail, Traditionally, we use each cycle of the impulse from the transmitter antenna to collect one sample in our trace. But with the real-time sampling, we can instead collect several samples along the trace for each transmitted pulse. So this results in a system able to collect the trace in a much shorter amount of time. As an example, for an 80 MHz antenna, the measurement of each trace takes approximately 300 times less than for a non-HDR antenna of a similar frequency. And as a consequence, we have the ability to stack the data more often, and this will of course increase the signal-to-noise ratio and provide us with clearer data. So for each pulse we transmit, we can actually gather several samples on our trace. And we need not that many pulses to actually describe the complete trace. And secondly, we have the benefit of an increased bandwidth with the HDR technique, which again lowers our noise floor. So a comparison at the bandwidth from a normal antenna and an HDR antenna, we can see that the noise is lowered and the bandwidth is getting broader. So with this lowered noise floor, we can access additional parts of the signal, which on the high frequency side provides us with a better resolution. And for the low frequency side, we access additional parts of the lower frequency spectrum, which gives us better depth penetration. So which are the biggest advantages to use a drone-mounted GPR? As we already heard, it gives us access to dangerous areas or other inaccessible areas, and it also speeds up the investigations. But there is, of course, plenty of disadvantages to use a drone for GPR measurement. The technique is based on unshielded antenna, meaning that the GPR waves are emitted in all directions. And by that also collecting reflections from all directions and not just from the subsurface. So when looking at GPR data, we must be aware of this situation, that the reflection can actually come from anywhere and not just from the subsurface. And we also use an antenna technique that is made for ground coupling. So the flight height must be limited. And as we have heard before, it should be kept at approximately 1 meter's depth, 1 meters above the ground surface, of course. So, okay, let's look at some data. All measurements shown in these presentations are made with a frequency of 80 megahertz, so it's quite low. The antenna elements, as you have seen, are approximately 1 meter long, and there's a transmitter and a receiver antenna, and they are separated with approximately 80 centimeters. So test one was made in a gravel pit and on 3 different heights, 140, 50, and 10 centimeters above ground. The highest elevation is on top, and the antenna closest to the ground is seen on the bottom. So as you can see that the number of air reflections is decreasing with flight height, and the penetration increases. So this is pretty much what you actually expect. When we fly high, we get more air reflections, and when we stay closer to ground, we have better depth penetration and less air reflections. In this case, we have a penetration of approximately 100 nanoseconds. So it's not that good compared to a ground measurement with an 80 megahertz antenna, but it's worth mentioning that this site was had been been heavy rains during several weeks before this trial. So even with these not that perfect ground conditions, we could see approximately 3 to 4 meters at the flight height of 1.5 meters. Test 2 was also made in a sandy area at varying elevation. We made the test ground coupled at 50 centimeter elevation and at 150 centimeter elevation. And in this area, the GPR conditions are close to perfect. As you can see in this ground coupled example, where we actually have data down to 15 meters and beyond. So if we look at the elevation of 50 centimeters, we can see that some structures are not as strong as in the ground coupled investigation, but we still can trace these sedimentary structures to at least 15 meters depth. And at an elevation of 150 centimeters, we see even more loss of details, as well as a small decrease in the depth penetration. Air reflection becomes more prominent, of course, and those need to be handled as in any interpretation. So if we change the direction at this elevation, 150 centimeters, from inline to crossline polarization of the antennas, we actually see an improved picture again. So now the data is again comparable with the flight height of 50 centimeters. So that is also something to consider when doing ground penetrating radar measurements from drone. It's the polarization of the antennas. Okay, so let's leave the soil and sand sediments and look at some peat data instead. So test number 3 was made in a peat area with 2 heights, 50 and 100 centimeters above the ground. And the bottom of the peat can actually be distinguished in both these measurements, but you can see it more clearly, of course, at the flight height with 50 centimeters. You need some more work to get it as clear in the 100 centimeters above ground measurements. So the peat bottom is seen at approximately 60 to 80 nanoseconds. And here in Sweden, we use a lot of peat for heat. So to fly a drone instead of using manpower and walk or use snowmobile is actually quite efficient. So one way of displaying these types of results from a peat investigation could be an easy Google Earth map with a color scale telling us how much peat we actually have in this area. And of course, this is an excellent ground for volume estimation of peat. And then finally, we have test number 4 for snow and ice. And these results actually just came from measurements done yesterday. So the processing is in no way ready. But even in more or less raw data, we can distinguish the bedrock at 1,200 nanoseconds. And that is actually 100 meters of ice. So even with the flight height of approximately 1 to 2 meters, we see nice features within the ice. And I would like to thank ATH in Zurich for both the photos and the data. So finally, to conclude, collecting GPR data using ground-coupled antennas will generally give more detail and depth, of course, than data from air-coupled GPR systems. However, as we have shown, there are many applications where drone-based system would be equally good to solve the geological problem at hand. So useful data, access in difficult terrain, and speed of data acquisition make drone-based GPR a very attractive solution. So we will continue the work to find new application areas, improve data quality, and also investigate the possibilities of other frequencies for drone-based GPR antennas. So thank you for listening.
Thank you.
Thank you very much, Jana, for your presentation. It looks like we have a question regarding your comment about cross-line polarization. And can you clarify whether or not you're saying that cross-line polarization is better than inline in general, or is it specific or only to certain types of surveys?
Okay. Most often, cross-line polarization is better when you want to detect hyperbolas. So when you want to look at the structure of the sand, the till, the moraine, then you can actually see the hyperbolas better. If you're only looking at layers, I think that it doesn't actually matter if you do it inline or cross-line.
Thank you. The next question is regarding bathymetry, and if it's okay, I would actually like to save that one for after our next presentation.
Okay, yes, that's okay.
As I think that might be addressed. If it's not, we can come back to it.
Yeah.
There's another question regarding gimbals and whether or not, I'm not sure if you want to discuss whether or not gimbals have been looked at with respect to the GPR specifically. I think the question is aimed more generally at all geophysical equipment on drones, but maybe you can address gimbals with respect to GPR specifically.
I have to think about that question, and then I can answer it in the question and answers.
Actually, that question was related to an earlier question regarding gravimeters, so it's not really relevant to the GPR discussion.
Thank you.
All right, well then, if that's going to be the case, without further ado, I think we'll introduce our next speaker. I apologize, Kian, we're a little ahead of schedule. I hope that's okay. So our next presenter is Kian Dawson. He is with the USGS, and he is going to discuss testing SUAS ground penetrating radar for hydrologic studies, results, lessons learned, and future direction.
Thanks so much, Morgan. I just want to confirm that you can see my opening slide.
Absolutely.
Good to go. Great. So my name is Kian Dawson. I'm with the U.S. Geological Survey Hydrogeophysics branch out of California. And one of the roles I play with the branch, our focus at the branch overall, is looking at hydrogeophysics, new and emerging methods, tools, and applications, and how they can be applied to USGS studies around the nation. And over the last few years, we've been working on integrating UAS-mounted sensors into that. And one of the priorities over the last couple of years has been GPR, and the initial applications for the GPR have been freshwater bathymetry. So I'm going to talk a little bit of an update about that work today. So first, I just want to acknowledge we've been flying and doing other testing across the country for a few years. We started in about October 2017, and it takes a village and a team. And I couldn't possibly list all the people who've been involved. There have been actually a few dozen folks helping make it a success in that field. So I just want to shout out to everybody involved in that. So what's our priority here? What's the context for the GPR bathymetry? For the USGS, we have over 10,000 stream gauges across the US, but we can't automate collection at all those sites. And so we still have a lot of people working in the water. For example, in 2017, USGS hydrographers made over 80,000 stream flow measurements. That means they were off a bridge, they were taking measurements off a bridge, they were in a boat, they were in the water, or something similar. And this kind of in-water work is one of the most dangerous aspects of USGS hydrologic work. So our goal really is to get people out of the water, out of the boats, get equipment out of the water, because when people and equipment are in the water, they're exposed to extreme temperatures, rapidly moving water, debris, unstable footing, rapidly changing water levels, water quality hazards. And so it's been a real priority for us in the last few years to look at non-contact stream discharge measurements. And in this context, non-contact for us is really focused on UAS. So using drones to collect the measurements that we need in the field at different sites around the country to estimate stream discharge. And what's our vision for this long term? We're still in the early stages of it. We've been doing testing for a few years with different systems, but our long-term goal is that we actually have a multi-sensor UAS system that allows us to collect combined bathymetry and stream velocity, and then those measurements are used to estimate stream discharge. So for stream velocity, we've been testing Doppler radar as well as video for large-scale particle velocimetry, and that video is both red, green, blue video, and there's also been some testing on thermal infrared, although the thermal cameras have to be pretty high-end, high resolution for the stream velocity studies. For bathymetry, we're looking at LiDAR and GPR, and really GPR has been our big focus over the last couple of years. And this long-term vision is that we go out, we have a hydrologic technician who's out in the field in states across the country. So basically that we have USGS offices across the country that have these systems. The hydrologic tech goes out in the field, collects automated surveys during either routine testing or during flood and storm events, that they are able to do some level of automated data processing during that time in the field to give them sort of a first order result. And during those surveys, we need safety to be a high priority for both the aircraft and our personnel. And so we really need aircraft systems that can deal with obstacle avoidance, situational awareness, terrain following, and long-term, our goal is beyond visual line of sight. So that basically you're actually sending off the drone to a remote basin, sends off, goes, collects its GPR track, comes back. And we also, for flexibility, because drones just won't work at all of our sites, we're also looking at alternative deployment options for non-contact methods. So an alternative to a drone might be if we put it on a fixed mount on a bridge, if we run it along a cableway, and I'll show you some examples of cableway testing we've done so far, or a crane off a bridge or off a boat. So for folks not thinking about streams and bathymetry very often, basically this is what we're after right here. So this is really sort of the low-hanging fruit. This isn't our end goal for drone GPR, but this is the high priority right now. And that's basically when we want to go out, we want to be able to capture the water, surface water, and then image the bottom and come up with this cross-sectional area. So a very simple measurement. We need the cross-sectional area of the transect flown on the stream. So GPR, why GPR? We know it can be used for surface and waterborne surveys, but part of our questions were, do we need a modified system that is optimized to be air coupled for airborne deployment? And so we a few years ago, started thinking about how can we put drones and GPR together. This isn't our first work in airborne GPR. So over 20 years ago, USGS had a non-contact stream gauging initiative that started at the time looking at helicopter use. And as part of that Hydro 21 initiative, they successfully demonstrated airborne radar could be used to map stream bathymetry. But the reality was that having a helicopter mounted solution just wasn't reasonable for wide scale application and use across the USGS. We can't be flying helicopters at low altitudes for routine surveys across the country. We needed something more flexible. So as changes happened and drones came more on the scene and became more readily available to us, especially in terms of Department of Interior operations, as well as FAA approvals, our office has been working on multispectral, photogrammetry, thermal infrared, and hyperspectral surveying as well. And USGS across the country has been using a wide variety of drone surveys. So once we were getting involved in this, we thought that GPR would be one of the sort of first geophysical traditional methods that we might be able to more easily adapt to drone-based. So around fall 2017, John Lane in my office approached Guideline Geo as part of a cooperative research and development agreement, which is a sort of a tool for us that allows federal and non-federal parties to share services and collaborate with external partners. And our vision for what we were thinking that we needed at that time, just thinking about the specifications of what we would want a GPR system to be able to do for bathymetry, is river cross sections, especially during floods. We wanted it to be able to work in, had to work in up to 30 feet of water. And we were looking for fresh water, and we originally set that fresh water as something below 800 microsiemens per centimeter. And as some other folks mentioned earlier, this is actually a big, this turned out to be a big challenge for a variety of reasons, which I'll touch on later. And the number is probably going to be much lower than the 800. And we wanted something small, so we wanted it self-contained so that it was basically platform agnostic. It would be able to be mounted on any multi-rotor system. And we didn't want to max out the payload capacity of the system because we knew we would want to be adding additional sensors onto it. And so we started this work in the fall of 2017. We really started actually flying in 2019. And so during our testing, we've operated around 10 sites around the US for testing purposes. And I've flown at about 6 of those sites. So the system we've been testing right now is a prototype, the 80 megahertz Guideline Geo Geodrone. It's about 4 kilos, and our typical field crew in the field has been a pilot, which is typically me, a radar operator. The operation of the radar console is separate from the ground control station, and we've needed 1 to 2 visual observers, and that's not necessarily a standard for all of our flights, but it's been a particular issue for a need for GPR. And we've primarily been interested in hexacopter, but for additional testing, we've also operated off of cableways. This is just a quick, to give you a sense of, this is a visual observer. This is Eric White from my office, who is actually operating the GPR. You can see the hexacopter we were using, and then you can see the GPR mounted below the body of the drone. And then this is me off flying. And so setting it out across the water. For the surveys I'm talking about right now, these were all pretty much active surveys, i.e. these were not automated flights. So I was actively flying. So I'm going to show you some samples from around the country, a few of the spots, just to show you some examples of some of the questions we're running into, some of the issues, some of the lessons learned. So Saco River in April 2019, typically we're flying, or one of the questions we're looking at is what height above water do we have to fly? The higher we can go, the more quickly we can go, and the safer it is. So we don't want to be flying immediately over the water surface. Typically what we're doing, if you look in the bottom right-hand corner, you can see this is actually a field site. I'm actually operating from this sandy area right here, flying all the way across. And the first thing you might notice on that other side is all of the trees are flooded.
Ja, men jag måste nog vara med på de här frågestunderna sen.
So maybe we could mute folks.
Nej, men ni får titta på nu. Alltså nu, jag ska inte bli...
Jana, your microphone is not muted. Thank you.
Thanks. So the far side was flooded. The trees were flooded. So our goal really is that we want a bank-to-bank survey, and that wasn't possible here. So the profiles that you're looking at right here are roughly the same transect. One was at a height about 15 feet. One is a height about 30 feet above water. And this is an out and then back. So you're actually looking at the x-axis as time. So it hasn't actually been converted to distance. And this matters because I'm flying manually, my flight speed isn't exactly the same throughout. So that's why your flight out and then back appears to be a little bit different. So really what we were aiming for from that, quick flight out and back, and since we didn't get all the way to the other side, we didn't do a full stream transect cross-sectional area. But basically we're trying to pick the bottom and the water surface so we can get this cross-sectional area. So that's kind of what we're aiming for with all this. So that same week, we also flew at the Androscoggin River, also in Maine. And you can see the site down at the bottom corner. For those of you who know John Lane, he is perched over here on the far side of the bank as a visual observer, making sure that I do not fly into the trees or into the bank. Situational awareness was a big challenge. So for this site, it was an out and back. So we flew bank to bank. So it's flying over land, then out across, and then I paused. So I paused in the beginning, we fly across, I paused on the other side over the bank, and I turned around and I flew back. So again, the apparent length is a little different because of different speeds of the aircraft. So from this, a couple things came up. One is that the stream bank geometry is very different on both sides. So near the launch, it's fairly shallow and increases gradually. And it was a fairly steep bank on the far side over here. So we can see that we weren't able to clearly identify the water's edge initially, but we're able to map some section of the water bottom at depths from about 24 to 12.5 feet. And typically we were collecting acoustic Doppler radar profiles at the same time. And for this site, that was probably within about 20% of the ADCP. So we felt that was successful for those depth areas, even though we didn't get the water's edge. So generally for the Androscoggin, we were successful imaging up to about 24 feet, about 20% of ground truth. We actually collected a complete drone-based discharge estimate. So we were concurrently collecting Doppler radar and large LSPIV for stream velocity. And we actually had probably at different times 4 to 5 aircraft in the sky at the same time conducting surveys. And they were operating independently with independent pilots. It wasn't acting as a swarm or anything like that. And the safety situational awareness was an obstacle in terms of when you're flying on the GPR, we didn't have any other sensors on it in terms of, for example, a camera or anything like that to be able to judge the distance to, say, the trees or as you come up the bank on the other side. And so that's required significant additional visual observers than we would realistically want in the field or be able to have in the field in the future. And one of the other issues is that once I'm flying down at these lower altitudes, I'm flying eye level in a lot of times, and became very apparent that the aircraft did not maintain, even though when the ground control station said that it was maintained a level height, that it wasn't. And so since we had folks out here at the Androscoggin doing surveys, GPS surveys, and they actually surveyed in the aircraft at different points relative to our launch location, and we found that it varied up to 6 feet. So it would say it was at the same, but it was often up to 6 feet off of that. So when you're talking about flying at low altitudes over obstacles, and whether it's ground or water, that's a pretty big safety issue. We also did some testing out at the Neversink River. We did some cableway deployment, and I also flew. So one of the things I just wanted to show on this one was that one of the techniques we decided in the field was that once we arrive and before we start our main transect, typically we flew up to about 200 feet so that we could get a signal. And this is just to show you that. So I'm starting off, I'm raising the aircraft to about 200 feet, and then I hovered there for a couple minutes. And this strong reflection you can see here, we're getting really nice, clear, surface water reflection of the top of the water. And that was really the case in most of the surveys we did. And then I came back down and the survey stopped at around 15 feet above water for some of the surveys there. We did try flying lower, and we've tried flying higher. And the question of what is the optimal height is kind of still to be determined. With the Neversink River, the water depth ranged quite a bit from, say, 0.2 to 3.5 feet deep. And for us, that ended up being a little bit shallow. So we got a clear return from the water surface. And since we're doing perpendicular to the river at this location, we are able to assume that the water surface is level, whereas we also flew parallel to the river. You can't assume that it's all going to be level. For this location, we decided that for the 80 megahertz antenna, a height of about 35 to 40 feet was optimal. Either that or it had to be super close to the water, which just isn't realistic in terms of most site deployments. We couldn't clearly image the water when it was less than sort of 1.5 feet deep. And so we think that the 80 megahertz antenna is really optimal for water depths over a meter. Last month, we did some additional testing out on the Gunnison River. So this test was purely by cableway. And so I'm not going to show you any data profiles here, but I'll show you some results. So this is a temporary cableway that USGS put up across the Gunnison. This is the aircraft. Oh, sorry, this is the antenna. And this also is the separate external GPS unit that we added. So we're still evaluating the data. One of the, we talked about specific conductance. We actually had to keep changing the site because even though I kept talking to folks about limits, when folks hear fresh water, they assume it'll work at any fresh water. And that's definitely not the case. So there were a lot of areas in this region that we thought of flying, but the specific conductance of the water was just simply too high. And so this was a good learning experience also for testing out the cableway more seriously and identifying some needs there. So overall, our outcomes for the last year have been, we've successfully demonstrated the GPR for stream bathymetry, but we still have work to do. So the 80 megahertz version is probably limited to water depths greater than 3 feet. And we really have to identify how to deal with the water's, accurately mapping the water's edge and steep banks. We're also working on lots of other applications. I kind of mentioned that the bathymetry I think of as sort of the low-hanging fruit. So we really want to map long-term the stream sub-bottom. We want to do conventional subsurface mapping. We've done a little bit of testing there. USGS is also collaborating on snow surveys. And so you can see in this picture, there's another radar system that we collaborated on with the University of Southern California and Sam Prager out there. And that was tested actually this March successfully. So we're pretty excited about that. So there are a lot of applications for the GPR, but there are a lot of challenges. So situational awareness is a big issue. We're flying below tree lines, we have flooded tree lines, we have overhanging canopy, the question of how close to the water do you have to get? And from here, we're really looking at the question of where do we go now? So we want to address some of those challenges. We really are, in the next few months, we're identifying and speccing out this multi-sensor platform, both in terms of the sensors, the specifications for the sensors needed, and the data standards associated with those. And one of the things, folks have mentioned before, and it's a common issue for when we're dealing with geophysics, is that, people sometimes fail to take into consideration the geophysical characteristics of the site. So if we're working a lot with folks who aren't geophysicists, they're not GPR experts. And so we need to work on our communication in that realm. And so one of the things we're doing is developing a decision support tool to help people evaluate where this may or may not be a valuable system. And that's it for now.
Wonderful. Well, thank you for that lovely presentation, Kian. I believe we have a handful of questions for you, and if Ron and Lori can help me field the questions, that would be very helpful. I just want to check real quick and make sure that our question about the maximum depth concerning bathymetry with GPR had been addressed. That was a question that came up right at the end of Jana's presentation.
We haven't maxed out our depth, so we've only tested up to 30 feet. But based on our testing so far, we think it can go deeper. So, we haven't figured that out, that upper limit.
Wonderful. And then the next question is regarding the use of unshielded antennas and how that might affect signal to noise ratio and accuracy of the findings.
Yeah, it's an interesting question. So initially we saw a lot of noise in the GPR data, but so we've worked with multiple prototypes of the system, and in the end, it actually hasn't been a significant problem. On the other hand, Morgan was actually out at the testing that we did at the Gunnison. I wasn't out there, but my colleague in my office, Dave Ray, was operating the GPR, and they actually had much more problems with noise there. And I think a lot of it was because not only did we have the cableway over, the cableway stands, there's trees, but also the narrow sort of slot canyon kind of issue. So that's a question we want to identify, because there's also interest for us using GPR for bridge scour. And so the question is actually, how close can you get? So surprisingly, though, in a lot of the places we've flown, it hasn't been a significant issue.
Wonderful, thank you. The next question is, do high amounts of suspended solids during flood events hinder the interpretation?
So that's an interesting question. So really, the question, we haven't done flood testing yet. We've been sort of working on system basics. So I keep looking for more optimal settings to hammer out sort of how the systems are working and basic flight parameters and optimization. So, but yeah, I mean, anything that's going to affect the conductivity, and it's not just storm events in terms of like suspended solids. One of the first flights actually that I did was in Denver on a pond on the Denver Federal Center. And it turned out that that pond got a lot of runoff from the roads. And so our initial just quick, like, let's go out and fly it. We had trouble seeing the bottom of the pond, even though it wasn't that deep, because there was so much road salt runoff for it. So that's when we're looking at trying to identify how do we help people sort of make a decision about where this is and isn't appropriate. And the reality is that, folks want to make drones in general a silver bullet, and it's not. There will be sites where this is going to work at and sites where this is not going to work at. And some will be somewhere in the middle.
Wonderful. We have a question about whether or not the USGS is exploring the use of waterborne unmanned vehicles. UAVs might be useful for swift water, but for still or calm waters, a drone boat might be more practical.
So USGS does use unoccupied underwater vehicles for other testing, but part of the goal of this particular non-contact discharge is to get stuff out of the water. So when you've got, especially floods and storms, you've got debris, you've got rapidly changing water levels. And so we're actually part of the specific goal of this initiative is getting instruments out of the water.
Wonderful. There are several more questions, so I'm going to apologize to the participants because I won't be able to get to them all in the next minute. I'm going to give you one hopefully shorter question. What kind of drone brand are you working with, and are they developing specific drone models for the USGS purposes?
So we have tested a few different ones. The prototypes that I mentioned mostly today was a specific 80 megahertz guideline Geo Mala drone. And so we have, as I mentioned, we collaborated and we approached Guideline because we had an ongoing cooperative agreement with them for research and testing of geophysical instruments. And so we approached them. And so we've had they're the engineers behind it, and you heard the presentation just now prior to me about it. And we've just been doing scientific testing out in the field for both UAS operations and trying to identify sort of optimal applications and data collection procedures. But there are other folks who are developing them. And for example, the snow drone that I also showed was built by the University of Southern California, Sam Prager. So there are different ones coming out that people are working on. It's actually a little harder to find some of the GPR info out there, especially because some folks are doing a lot of UXO work related to military work, and that information can be a little bit harder to track down.
Wonderful.
I'm happy to answer the other questions later, though.
Thank you, Kian, for your answers. And without further ado, I'm going to pass it over to Ron to introduce our next speaker.
Thank you, Morgan. Thank you, Kian. A very, very interesting talk. And you guys are doing some great work. The next speaker is Christoph Bras. He's with SPH Engineering. His title of his presentation is GPR on a Drone, Practical Experience Gained in the Past 2 years.
Yep, thank you, Ron. So I just now shared the screen. So let me know if you can see the presentation.
Yes, it looks great.
All right, that's perfect. Hi everyone. I'm Kristaps from SPH Engineering from Latvia. And so the title of my presentation is a GPR on a Drone, Practical Experience, which we gained in the past 2 years. So I think first, let me just give you a bit of background on us. So basically, we are a software development and UAV systems integration company, and we were founded in 2013. Among other projects, we started experimenting with using GPRs on drones in 2017. And so by 2018, we already had our first drone GPR integrated system that had an onboard computer, and it did support also automatic data logging. And so in the same year, in the summer, we went to Greenland on our first expedition there, where we actually did find a World War II fighter plane, so a Lockheed Martin P-38. And I'll mention this also further on down the presentation. I'll show you some data from this. Then in 2019, we implemented true terrain following, and we also expanded the range of supported GPR antennas. So basically, currently it's supporting RADSys zone, 500 and 1000 megahertz antennas, radar team antennas, which are more lower frequency, as well as some double antenna configurations. Also, in January of 2019, we went to Peru to also do inspection of some archaeological sites over there. And this also I will mention later on in the presentation. And so last year as well, in the summertime, we went on our second expedition to Greenland, where we also did search for the somewhat legendary Grumman Dock World War II aircraft. And so currently this year we have redesigned the user interface, and also we did add support for additional sensors such as gas detectors and metal detectors. So when we did develop this our system, so some of the main challenges which we faced was firstly, you do need to perform low altitude flights in order to get some good quality GPR data. Also, of course, data logging has to be started and stopped automatically, and that the GPR data does need to be fused together with the data from the drone's GPS. Also, what we discovered is that for data processing, it's necessary to insert marks inside the data so that everywhere where you have waypoints, so let's say where the drone is turning, so that later on you have these marks according to which you can split the data. So I think it's important to make this kind of disclaimer from our side that we do not think that airborne GPR surveys are meant to totally replace the standardized methods of using GPR. But what they can serve as is they can serve as an additional method of performing GPR surveys in certain scenarios when the circumstances allow it. A good example is actually the zoned 12E 500 megahertz antenna, which you can see here in the pictures. So on the left side is pictured on the drone, and also the second image from the left. But actually also it can be used on ground-based surveys. So you can have the same radar and basically use it either on the ground with the cart, or you can use it on the drone. So our current turn following system with the GPR, it compromises of these components. So firstly, obviously you do have the drone. In our case, we do use DJI M600 Pro drones, but similar drones also can be used. Of course, also you need to have the GPR, and so preferably a GPR that's light enough for the drone to lift. Then also in our system, we do have the data logger, which basically it logs the data from GPR, it fuses it together with the GPS data, as well as it helps with terrain following. Next, we do have also the altimeter, so either a laser or a radar altimeter, and these are used for terrain following. And then we also have the software. So this is what we have developed ourselves. It's actually, let me maybe switch on over to the next slide. So here on the left side, you can see this is our flight planning software, UGCS, where you can plan the missions for your drone in 3D environment. And then on the left side, what you can see, this is called the custom payload monitor. So here you can actually set the drone in terrain following according to a certain height and speed. And also you can monitor the data from different sensors is coming through. So I think now maybe let's switch on over to our expedition in Greenland in 2018. So at this time, we're still kind of experimenting with using GPRs on the drone. And so in this expedition, actually, we did have two teams over there. There were us who were using GPR on the drone, which can be seen here in the picture on the left side. And then there was actually another team who were using ground-based GPR, which you can see there on the right side. And so actually what happened was that we got quite lucky because while the other team was still doing the ground-based survey, we actually did manage to do the first flight with our drone, with the GPR, and managed to get the data. And what we actually found is that on the very first survey line of the very first flight, we did manage to catch the anomaly. So here you can see where you have the marks, so 1, 2, 3, 4, 5. These are actually parallel survey lines. So you can see that on every survey line at the same location, there is the anomaly. And so this anomaly was actually later confirmed to be the aircraft, which was confirmed by drilling small holes and then obtaining hydraulic fluid used in US aviation. And the depth of this aircraft is actually at a bit more than 100 meters below the ice surface. And so this was detected with the Cobra SC-70 antenna. So here, these are not our images, but these are images from a similar aircraft, actually the same model aircraft from the same squadron at the same location, which was recovered in 1992, where this team, they basically melted these giant holes, then they rappelled down, disassembled the aircraft, and actually brought it up through these holes, then brought it to the United States, and currently it has been already restored to flying condition. So hopefully the aircraft that which we found 2 years ago, hopefully that's going to have a similar fate. So also we did go to Greenland last year as well, and there we also did a few flights, and one of these can be seen here. So this was a flight where we did snow profiling. So basically the drone was flying up the hill in terrain following mode. We used the 500 megahertz antenna. And so what you can see here is that it did measure the thickness of the snow blanket. So leading up to the peak of the mountain, the depth of the snow, or the thickness of the snow blanket, was about 2.5 meters. And at the very top, it was actually even up to 17 meters. Also, during these years, we did do some tests where we basically kind of compared the data quality when flying at higher altitude and when flying at a lower altitude. So here, what you can see in this slide are two pictures. So the image on the left was done at 2 meter true terrain following altitude, and the image which you can see there on the right, this was done at 7 meter altitude. So in certain scenarios, when the vegetation is quite high, then it might not be possible to fly quite close to the ground. And so actually it was interesting for us to discover that even when flying at, say, 7 meters, it was still possible to detect these targets. And so in this case, these targets are actually two natural gas pipelines with a diameter of about 0.7 meters. And in this case, we did also use the 500 megahertz zoned antenna, and the soil in which the pipes were laid into, this was basically dry sand. Also, we have developed our own software for analyzing GPR data. This is called GeoHammer, and actually we made it open source, so it can be downloaded by GitHub and tested by anyone. So the GeoHammer has been developed with the following intention, so that when there are some people in the field who are simply flying the drone, people who are, say, not geophysicists, they just want to make sure that this data is okay. So then they can use the software and basically see whether the data that they have gathered, whether it is usable. So in this case, in this image, what you can see is that here on the left side, this is the map, which can be seen. This is one of our test polygons. And so there on the right side, we already actually have placed these flags at locations where we have the targets. And as you can see, the targets have been correctly identified. And yeah, so this is kind of how the software works. It's a very simple tool, which isn't really designed to replace like fully blown geophysical software, but it can be used as an additional tool. So also in 2019, we went on another, I suppose you might call it an expedition to Peru, where we basically worked with archaeologists who, they were searching for different artifacts and ruins over there. And so in this picture, what you can see is the DJI M600 drone with the Radisys on 500 megahertz antenna while flying in automated true terrain following mode. And so after performing flights in this location, we did discover some potential archaeological artifacts here, but we're still waiting for the permission to excavate this area. So once the researchers get this, once they excavate this, then hopefully we'll also be able to provide some more concrete evidence that this was indeed there and this was discovered by the GPR. And so another thing, what we're doing is we're actually building now, we have already built our GPR test site. So here you can see that next to our two other polygons, normal sand and so just like black sand polygon, now we already have dug a few targets. So here, these longer lines, these are pipes made from different materials. So in yellow, that's a reinforced concrete pipe. We've also dug stainless steel pipe, then empty PVC pipes and water-filled PVC pipes. Similarly, we've dug metal barrels in both horizontal and vertical directions, as well as empty and water-filled plastic barrels. But since actually this site was only completed this September, then since it's somewhat of a rainy season now in Latvia, then we haven't actually been able to use the GPR properly in this location, but we have been able to use other sensors here. So here you can see the targets themselves. So this is the steel pipe, stainless steel pipe, and plastic barrel. And here you can see the vertical plastic barrel, reinforced concrete pipe, as well as a PVC pipe, which was later filled with water and sealed. So since, like I said, we're not yet able to use the GPR in this case on the site, then we did use some other sensors. So now we actually have also developed support for the Geonyx EM61 light metal detector. And so here you can see how it looks like when it's mounted underneath the drone. And after doing the flight, and then when stitching all this data together using Oasis Montage software, so here you can see the outcome of this on the right side. And you can see that it did manage to correctly identify all of these metallic targets. And similarly, we have actually also been experimenting with using magnetometers. We've used the Magaro magnetometer, and also here in the image, you can see the Census R3 magnetometer, and also it was flown over our area, our test site, and also did manage to find the targets. So to kind of put it all together, so what are the advantages of using GPR on the drone? As already mentioned in previous presentations, one of the main advantages is that it also has higher survey accuracy. So a drone is able to hold its speed and heading with a higher degree of accuracy in automatic mode compared to when these surveys are performed, say, on the ground. Then also, of course, it does increase the productivity. So in a single day, by a single team, you can actually acquire tens of kilometers of profiles with GPR data. And using it on a drone actually does also mitigate the risk for personnel. So the work actually can be carried out without having to walk through the survey area. And it also is more cost efficient since, as we all know, time savings do translate to cost savings, also known as time is money. And so drone surveys also do save money in this case. And also, it is suitable for uneven terrain. So a drone with the GPR is capable of performing the survey while following the terrain almost anywhere. And so now keep these words in mind, while following the terrain almost anywhere. And let me take you to the next slide. So here, this was actually sent to us. I think it was sent to us today. And so here in the first image, you can see, well, we might not be able to see that well, but in the middle of the image, there is a drone with the GPR that's heading towards the waterfall in terrain following mode. And so here you can see that on the next image, well, somehow it did luckily manage to stay above water, but we'd not recommend using the drones with terrain following in these extreme scenarios. But then again, it's probably better to use a drone in this case than to use a manned survey. But of course, using GPR on the drone does have its limitations. So one of the first limitations is that GPRs do, of course, have certain weight to them. So this means that you do need to have a drone that's capable of lifting the GPR up. So this actually excludes small UAVs in most cases. And this means that industrial grade drones do need to be used for carrying the GPR. Also, most drones, they do have a limited flight time. So the DJI M600 Pro drone with the GPR can fly for only about 15 to 20 minutes using a single set of batteries. But this problem can actually be solved by using multiple battery sets or even using a hybrid drone that's using a petrol engine on board. We've also discovered that you do lose a bit of penetration depth when performing airborne GPR surveys. And according to our data that we've gathered, this loss is approximately 50%. Also, flights do need to be performed at quite low altitude. So here the general recommendation is to fly as low as possible. So with the 500 megahertz GPR, the recommended flight altitude is 1 meter or 60 centimeters between the antenna and the surface. And I remember that in one of the earlier presentations, it was mentioned that, so according to the legislation that you have, it's not sort of legal to use the GPR on drone in many places. But actually, when using it with true terrain following, you are able to kind of keep within the 1 meter altitude that's mentioned in the regulation. So here, actually the antenna would be 60 centimeters above the ground, which would make it legal. And also the 500 megahertz antenna, which I showed here, it is certified for using in the US. And then also the final point is that space is required for flight safety and maneuvers. So this means that it's oftentimes hard to use the drone in some tight areas. And so, for example, using it maybe in some more urban environment, that might cause some problems. So that's also something that you need to keep in mind. And so the conclusions from this is that firstly, using GPR on drone has actually demonstrated the ability to raise the productivity of the GPR data acquisition, since the drone is able to do these surveys faster than when performing them, on the ground. But with that said, the drone can't really serve as a replacement for traditional GPR survey methods, mainly because it's necessary to perform low altitude flights, which are not possible in areas with tall vegetation. And also, like I mentioned, in the case with our test polygon, a very wet upper layer of the soil can actually make medium or high frequency airborne GPR systems somewhat useless, because only a very small part of the energy from the impulse will penetrate that. And but I think that airborne GPR surveys definitely do have a future in certain applications and conditions when they are met, such as, for example, freshwater bathymetry, or also when flying over wide open spaces or areas with low vegetation. And thank you. So that's it from my presentation. So I guess now we might take some questions.
Thank you, Christophs. There's a bunch of questions. Morgan, can you read them?
Yes, I can read them. And some of these are actually excellent lead into our discussion portion. So Christophs, I'm going to pick some that are relatively specific to your particular work, and then maybe we can use some of these other ones to kick off the discussion. Christophs, in your Greenland 500 megahertz UAV GPR data sets, were variable ice densities observed? If so, were these the product of ice age or other factors? There's more to that, but I'll start with that part.
Yeah, well, actually, it is somewhat of a complex question. So I'm not a geophysicist myself, so I can't really comment on the ice. But from the data, we did find that, well, later on, we did do kind of, we measured the snow thickness and did match what we got in the data. But it seems that over there, at some points, we did find in the data set that the snow layer basically did have varying degrees of density.
Wonderful. Maybe, Neil, maybe if you have additional questions, you can follow up with Christophs on this towards the end. There was a question regarding whether or not you have tested GPR and terrain following in steep mountain terrain, specifically slopes steeper than 20 to 30 degrees.
Actually, if I can go back to the case when we used it in Greenland 2019, so actually in that case, the drone was flying up the mountain. So in that case, I believe the elevation, I think it was steeper than 20 degrees for sure, maybe even near 30 degrees. So in that case, yeah, we did use it in that scenario. Of course, you also have to keep in mind what speed can you do these surveys at. And so when flying up the mountain, we use the speed of 2 meters per second.
Thank you. Sorry, there's a lot of questions. There was a question about using the UCGS software. Do you find you need to do a pre-survey with photogrammetry to get a reasonable terrain model first? How available are terrain models for remote sites?
One example which I can mention is that in some cases, it does help to first, let's say, do a photogrammetry of the area, and you can get the map of it. One case was when we did some work with like World War II archaeologists back, but it was here in Latvia, where basically they were searching for burial sites. And so then we did do a photogrammetry of the area, but we did not do this for the elevation. We basically did this to get the map of the area. And then once we saw the map, and once we saw maybe some obstacles that were there on the ground, maybe not necessarily obstacles, but some certain objects that might be shown in the GPR data, then we were able to compare the map which we got with the GPR data which we got. But going back to the question, so does it help to get terrain models? So you always have to keep in mind that these terrain models will not always be accurate. And this is actually the reason why we ended up developing this true terrain following mode. So the drone is simply able to use the altimeter to keep to the terrain. So, yeah.
Wonderful. Well, thank you. I think we will take this moment as a chance to kind of transition into our discussion portion. Like I said, there are several more questions, but I'd like to open them up to all of our presenters. I know that some of our questions have already been answered in the answered section of our Q&A chat. If you'd like to bring up a question again that was already answered but would like to hear from more presenters, please feel free to announce it again. We are in the process of migrating everyone over so that you can now actually ask your questions out loud. If you do not want to ask your question out loud, that's okay. Just let us know. You can either send it to Ron, Lori, or I specifically, or if you don't ask it, we can also read it out of the Q&A portion already. Lori, do you want to add anything before we start answering questions?
Yes. Once you're moved to where you can actually ask your questions directly and speak to each other, we ask that you raise your hand in the little interface. It should be at the bottom of your or next to your name. That way, we're not talking over each other.
Wonderful. Thank you. And Ron, do you have anything you'd like to add before we begin?
No, actually, I think that it's time to begin the discussion. So I think we've got some really good questions to begin the discussion with. So I'll let you choose which ones we want to throw out there.
All right. Well, the first question that I figured I would pose to Christoph, Jana, and Kian is regarding which applications do you think will be the biggest for drone GPR in the future?
If I can start, I think that the estimation of snow will be quite huge to be able to estimate the amount of water filling our water power plants for the energy.
Wonderful.
Can I comment? I'm Alexey Dobrovolsky from Space Engineering, the same company as Christoph's. So we can divide possible applications between possible from technical point of view and also most interesting in terms of usefulness. So most simple applications are snow ice profiling, of course, and also freshwater bathymetry. But from our point of view, freshwater use of GPR for bathymetry is not very optimal. So we see only two reasons why GPR is better for bathymetry. First is high speed of water, and like on the images which were demonstrated by Christoph's. And second, when water is covered by ice. So in such scenarios, you cannot use a casounder, which will provide better and more precise results compared to the GPR. For ice snow profiling, yes, it is absolutely obvious applications, but also in theory, GPR on the drone can be used in for any applications when normal GPR used, if conditions allow. So that means low vegetation, white area, and we have quite big loss of penetration will not prevent possibility to reach the target of survey. So for example, if in the same area from the ground you can reach up to 5 meters, that means that from drone you will have maximum 2 or 3 meters, and if it is enough, you can use the drone. And also there are a lot of specific applications. I saw questions about searching for landmines, for example. It is a very complicated area. So we spent a lot of time in experiments, even together with customers, to find a way how to detect landmines and not to get to high level of false positives. So currently, I should say that we don't have technology which can be used in the field. Technically, we can detect small objects
starting from big anti-personnel mines or anti-tank mines. But the rate of false positive is too high, and such system will be absolutely useless in the field. But yeah, for underground utilities such like shielded cables or pipes, GPR on the drone is good, again, if conditions will allow to use them.
All right, thank you.
Hey, Morgan, I can give a quick comment on that too. So one of the things we've been looking at is talking with what USGS scientists across the country need. So we don't use GPR in the full range of GPR applications. But when you start looking at the amount of stream gauging and river monitoring that happen and stream monitoring across the US, at least, and actually, and internationally, for us, the bathymetry is sort of that low-hanging fruit because there's such a large need, and it's a real drive in terms of safety. So, our vision is that we have water science centers in every state in the country, and that each water science center has a collection of, this multi-sensor stream discharge drone unit that's just a part of, one of the things in the back of the truck. Folks go to the sites, whether it's routine monitoring or during a storm event or a flood, and it's used. So we see a lot of interest in that, both in terms of the USGS needs as well as externally, and in terms of talking with state and local cooperators, things like snow surveys, snow water equivalent, ice jams and things like that are also a high priority. And a lot of that focus, as you can see, is really about human safety. So how to sort of hydrologic conditions that are affecting our potential safety.
Yes, I fully agree that it is wide area of applications for GPR, I mean bathymetry, especially in case of high speed of water. We also supply the systems with sounders on the rope, but such systems has limit around 1 meter per second of speed of water or speed of flight. So that limits application of drone system as a sounder by lakes, ponds, or some rivers where is not strong current. Yep.
All right.
I think there's some other questions to pose. One of them that I'm reading is, what are the technical problems inhibiting the use of shielded antennas on drones?
Oh, I'd love to answer that one. Or Jana, do you want to take it?
You can take it.
Okay. So we have to be careful when we talk about shielding antennas with radar. There's a misconception that the shielding is a directionality of the radar. It isn't. I mean, a bow tie antenna is still omnidirectional. The shielding does bring down some, brings it down by a few dB. It is not a perfect shielding in the first place. So shielded antennas are partially shielded. Yeah, the technical limitation is you need a Faraday cage that's, half wavelength, and it's rather large. So at 80 megahertz, that would be ludicrously large to lift from a drone. So that wouldn't work, but there is an alternative to that, and we don't have to use bow ties or dipole antennas. So if you got the right frequency, for example, Kian showed a brief picture of a Vivaldi antenna on a small drone. Now that Vivaldi antenna seemed to be in the 1.5 gigahertz range, which is a very small, neat little antenna. Those are very directional. So if you could design a Vivaldi antenna from a drone, that would give you your directionality and reduce the side lobe effect, which would ameliorate some of the problems we have with above ground objects. The problem with Vivaldis are the mouth of the Vivaldi. It looks like a trumpet, right? So the mouth of the Vivaldi is at your lowest frequency. With 80 megahertz, that would still be, it would look like the size of a movie poster, shall we say, but you could put holes in it to make it somewhat aerodynamic. But that would be a question for the drone guys. How would you lift 2 of these movie posters? You can imagine, say, 1 meter by potentially 2 meters sheet of metal up into the air, or at least 2 of them, because you'd need one for the transmitter, one for the receiver. I suppose you could make a monostatic system and have 1 poster. That would work. That would solve a lot of problems, and you'd get around the shielding issue. I just don't know how aerodynamic that would be.
Very interesting. Another question is, at what accuracy can the depth of the pipelines be determined? I guess that's a challenging question. Nobody wants to pop up and take it at this point.
So,
But,
okay, if
but
nobody
answer
wants to
is
answer
the
that,
same. Sorry, Jan. Answer is the same as with terrestrial survey. Absolutely the same.
I think
So it depends on frequency, on the medium around pipe, because it will define length of wave in medium. So, but short answer, with drone, we will get approximately the same accuracy as in case of terrestrial survey, especially if a precise altimeter was used during the survey.
Yeah, I actually, Alexei, the most geophysicists would answer that it depends, and it depends a lot on.
It depends. So I was very accurate in my answer. The same as.
Okay, the next question is for Christophs. Does the GeoHammer produce time slices of the data?
So GeoHammer doesn't really produce time slices of the data, but so what it can do is, firstly, it can so once you place the marks in the data according to the anomalies, then you can produce a KML file from that with coordinates of these anomalies, and also it can actually produce a heat map of the area, so you can move it to the certain parts in the data, so to a certain time range, and then it can produce a heat map of the anomalies in this area.
Okay, so what is the heat map actually representing?
So it's basically representing sort of hotspots, if you will, in the data. So kind of locations where there are certain anomalies.
Okay.
From technical point of view, it is almost the same as time slice, but we don't use gridding, any gridding algorithm. So we just summarize amplitude in certain point, and make a spot bigger and brighter depending on summarized amplitude of reflection. So it can be treated as very simple implementation of time slice. Okay.
So it's sort of an aggregation of all the times, and then you're bringing out the highest amplitude.
Yep, exactly.
So is there an upper speed limit of the drone when coupling GPR and GPS data?
So essentially, so currently we have two methods of flying with the terrain following. Method number one is that you're flying a bit slower, and so here, let's say if maybe the terrain is changing a bit more, then you can fly to, let's say, up to 3 meters per second. And then what our onboard computer does, it places waypoints quite often, so the drone can adjust its altitude. But it's also possible to, in case you maybe want to perform the surveys a bit faster, and maybe there aren't really too many obstacles in the way, then you can actually make it so that you can simply place one waypoint, let's say at the end of the survey line, and the drone will fly kind of somewhat straight to that point while adjusting the altitude. And in both of these cases, of course, it will stitch the GPR data together with the GPS data from the drone.
Could I just add to that comment? And this is a question we get quite a lot. The speed of a GPR survey, what nobody talks about is the latency of the GPS itself, right? So the satellites are sending signals at 1 hertz, and some of them will interpolate, some of the receivers will interpolate to 10 hertz or 20 hertz. But the point is that the new satellite updates are only coming at 1 hertz, and there's a latency built into even the most expensive GPS RTK receivers that could be up to 1 period between GPS readings, right? So you could have a latency by the time that NMEA sentence is written to the radar trace and married together of up to 1 second. Now, if you're traveling at 3 or 4 meters a second, that means your actual positioning could be off by 2 or 3 or even 4 meters. And it's a variable problem. It's very rare that we see anybody talking about that, but that is something to consider when you're looking at very high speed surveys, is the latency of your GPS system.
Yeah, the issue of GPS systems is one that I'm not working as closely on, but USGS is testing a variety of external GPS systems for the question of how accurate do we need to be and how accurate can we get and what's involved. And for us, there are two pieces. One is for georeferencing the data after the fact, which is kind of what you were referring to. But there's also the other question of accuracy of the aircraft location vertically and laterally for flight operations for automated flights. And so, yeah, so that was one of the things they were actually testing in the Gunnison, is looking at these different external systems. And it's, in terms of speeds, we've been flying, I've flown in terms of the GPR up to 5 miles an hour, but, we do tons of other surveys at much higher speeds than that. So probably 3 times that speed. So, our ideal would be, we've been flying slower for safety reasons, because when you're flying that close to the ground and you've got a lot of obstacles, how fast can you go is sometimes a basic safety concern. And that's a real issue with some of the drones.
How fast do you fly, Kian?
For the GPR, I've typically stayed between like 2 and 4 miles an hour. For my multispectral and thermal IRs, it depends very specifically on the height and the sensor we're using, but anywhere from usually 10 to 15 miles an hour. My goal is usually how high and how fast.
Okay, so when you're really close to the ground, you're flying much slower.
Yeah, for us, it's been a safety issue. If you're especially like flying over water. So, when you're flying at 400 feet or 300 feet, you're looking up and you've got this clear line of sight. But, when I'm flying a river, I'm typically going down a stream bank. And so I'm actually looking down on the aircraft that I'm flying, and I don't have that straight eye on visual of the air gap. And so given the sort of unreliability of some of the aircraft in terms of its sort of fluctuations up and down while they fly, that's it's that safety concern that it's going to sink, basically.
Right.
So I don't want to hit the water, and I don't want to hit a tree. So.
Okay, so you're flying it purely with the RTK GPS at this point?
No, actually, for the work we've been doing, we haven't worried that much about for the GPR. We haven't focused on the GPS. So that was one of the things we're looking at specifically in the Gunnison data we just collected a few weeks ago, and we haven't gotten the comparative GPS data to compare to the onboard system GPS and the prototype that we were using.
Okay. Okay. This is a question that is for Elizabeth. Elizabeth, is the software, the sequence software, going to be integrating GPR results or processing into your package?
Well, as for all other solutions, I would say if the demand is there, yes. Do we have it in our roadmap at this very moment? No. And that's part of the reason why we try to keep an eye on what type of sensors are being used, so that we know how to cater to the needs of the industry.
Is anybody, were there any other questions that we should
we have a attendee who has their hand up. So Sean, Marek, if you'd like, please unmute yourself and ask your question.
Okay. Hi. Yeah, a quick question for you guys. I've heard lots of discussion about horizontal accuracy and precision, but I haven't really heard much talk about the vertical accuracy and precision. How are you guys measuring this, and how accurate is the GPR in the vertical?
For the GPR, the vertical accuracy is said to be, as a rule of thumb, 10% of the measurement depth. But then, of course, we have the problem of deciding the height of the drone.
So how do you address that at this point? The height of the drone? The height of the drone or the height of the sensor?
Yeah, using the RTK GPS on the drone, that gives us the resolution of height. So that's a problem. But for me, ground penetrating radar measurement and geophysical measurements overall, it's always a question of application. If we are looking at archaeological application or utilities, we really need to be precise, but for layers deeper down, we always measure a volume. So we have an uncertainty already in the way we actually measure the ground conditions. So depending on the application, we need to be more or less precise regarding all of these GPS positioning of our measurements.
So is it just as a follow on to the GPS positioning in the vertical direction, what kind of resolution or precision do you have with their current drones you're currently using? Is it, let me rephrase that. Are you looking at 1 centimeter, 10 centimeters, or 1 meter resolution?
I think 10 centimeters.
Okay, and
yeah, for the vertical precision.
Okay, and you're using the RTK or GNSS to
Yep.
provide that resolution.
Yeah.
Okay.
All right, Jeff Pettifer would like to ask a question. So Jeff, if you'd like, please unmute yourself and ask your question.
Yeah, thanks, Laurie. My question is a general one in terms of XYZ navigation and accuracy. About 3 years ago, a client asked us to do a airborne GEM system. This was well before some of this was a very early days using a helicopter type system. The project didn't go ahead, but we were looking at all the problems we had to solve. One of them was variable grass height, variable bushes, and occasional tree obstacles. And the area that we had to survey was greater than line of sight. So I'm just wondering, what is the current state of the art of integration of the IMS systems, the terrain clearance systems, the vegetation detection, grass or bush top or tree top detection, the accuracy of RTK, the lag that has been raised, the ability to detect bushes ahead of the drone that you might have to skirt around, or do you have to do a photogrammetry survey manually of the site first, pick out where the trees are and replan your flight lines around them? Just a general question of the logistics of being able to maintain the height and also the survey feedback of all these systems. You know, is there sort of oscillation in the altitude, which then translates into detector noise, whether it be variable clearance of GPR, the magnetics, motion noise, whether it be EM clearance and so forth, EM detector clearance and so forth. You know, what is the, in other words, what is the sophistication of the integration of all these systems to avoid obstacles, avoid grass, maintain a stable terrain clearance, etc.?
Okay, I might address, sorry, Ian, go ahead.
Yeah, so this is actually what you're describing is what we've identified as one of the biggest obstacles for us using the GPR for bathymetry flights, because we have, you know, you can't use a DEM. You can't even necessarily rely on a DSM that you just generated for the site because the water levels are changing, can be changing over time. So I've done surveys at locations where, you know, over the course of the day, the stage of the water may be changing by several feet. And so if you're only flying 5 or 10 feet above the water surface, that difference in surface is going to matter pretty big. So really what we need is this integrated, not only obstacle avoidance, but sort of 360 sort of situational awareness and real-time information about that height. And so for us, that's one of the things we're working on right now is identifying that integration because we don't have it. And the software that we've used for flight planning and operations doesn't do terrain following. But like I said, even if it did, that DSM or DEM wouldn't be adequate for our hydrologic surveys. It might work over sort of static ground or dry ground, but for snow and water, it's just not a reliable resource.
So maybe if I can add a bit to this. So like the way we are currently using our true trend following is that it's used in somewhat of a basic way, in the sense that the altimeter itself, it's basically placed on the forward part of the drone, so on one of the front arms of the drone. So this means that as long as you're not flying too fast, so let's say you're flying at, for example, 2 meters per second speed, then the drone is able to adjust for, let's say, some small vegetation, some bushes, and the drone can simply go upwards. In other scenarios where, let's say, you might not want the drone to adjust the altitude, you might want it to stay, maybe ignore some smaller objects, we also have a hysteresis parameter, which basically allows you to set sort of this margin within which, if the altitude changes, the drone will not really change its own altitude. But as for detecting targets which are kind of in front of you, I think that's a bit more of a development for the future. So I see that maybe in like the upcoming years, what might happen would be that there might be some more systems that would use some more forward-facing sensors to maybe try to also detect some obstacles that might be in front of the drone rather than underneath it in real time, and well, thus make the drone already kind of think ahead what it will do when it approaches this obstacle.
Okay, the first person to have their hand up is Gary Young, and then we'll follow with Remke Van Dam. So Gary, please unmute yourself to ask your question.
Hi, thank you for doing this, by the way. It's been very enjoyable. I wanted to touch on some of the positioning questions in GPR surveys that have been talked about. As an old hand at GPR, I can see that regardless of your knowledge of your height above ground, which I think is an engineering solution that will be able to solve the geophysical problem of knowing with accuracy the vertical prediction of something that you've measured in the subsurface is, of course, the difficulty. Because GPR instruments measure their anomalies based on time, not depth. And in order to get the depth, you have to know the dielectric permittivity of the ground that you're under. And so what everybody does is they make a guess as to what that's going to be in the area that they're working. And I can tell you that your depth, if that guess is very wrong, that depth can be way more than 10% off, way more. And so that's really the vagary that you have to deal with. And on a survey like this that could cover so much ground so quickly, that will be an issue of knowing how good your depth predictions are going to be. I'd also like to touch on something that Jan talked about, which is really an unspoken problem with all of these, and that is the latency in the GPS. That is a big deal. We built a complicated system to measure utilities with the old GSSI TerraVision system, and one of the things we realized early on in our testing is that if we drove too fast, our positions were wrong. And what we discovered was this latency was the problem. And I think my team at UIT is the only ones that ever gave an engineering solution to solve that problem. And we actually got that completely figured out with a combination of hardware and software, but it was not trivial. So just points to be taken there. I think the surveys that we're talking about here, at least until we get to looking at something the scale of a utility, I don't think knowing your position or your depth with great accuracy is the key question at the moment, but I'm pretty sure in the future it will be. So thank you very much for your time.
Can I just add to that we have had a couple of questions regarding the frequency of antennas related to utility detection and the accuracy for detecting items on the scale of landmines and utilities. So if our panelists want to kind of add on to Gary's comment, this might be a good time to address those.
Okay, I'll take that. So obviously, just as in ground GPR, the frequency is a function of the resolution you want and penetration. And as Christoph has indicated, you know, I think in a very, very best case scenario, you're looking at about 50% penetration, but that's entirely dependent on the water content of the soil, so how much reflection you're getting, as well as the conductivity of the soil as well. So, you know, whereas you might use a 500 megahertz antenna to look at a pipe that's 2 meters deep in a good environment, that may not be sufficient to get you that pipe image from 1 meter altitude. The other issue, actually going back to our dielectric constant and getting that accuracy of positioning, is it really depends on what angle you attack that pipe at. For example, in the case of utilities detection, if you were to cross it at a non-perpendicular angle, you could skew your results when you're doing your hyperbola detection, right? So we're looking at the arms of the asymptotes of the hyperbola to give us an estimation of your dielectric. And if you're not crossing it at a reasonably right angle, then that's going to be underestimated or overestimated, I suppose, and you'll get the wrong depth. So, you know, there's a lot of issues at stake when we're looking at very precise positioning for utilities detection, and I don't think we're there yet. The big one being just the RTK positioning, be it the accuracy of the RTK or latency issues, and then add that it's an additive effect to the vertical issues of not having adequate resolution, because we'll need lower frequency antennas to get through the challenges we have of the mirror effect of the ground. So you go lower frequency for that, but that decreases your vertical resolution in pipe detection.
All right. How about we let Remke unmute himself and ask us another question?
Yep, I'm unmuted. Let me also quickly start my video, just to show people that I'm not in my pajamas, despite the ungodly hour here in Perth, 2:45 in the morning. Thanks to the speakers for the very interesting talks, and for SEC, of course, to put this on. Very, very nice. So I have worked with GPR all my life, and I have nothing against it. But it's obviously quite challenging when you pull it off the ground on a drone, because of what has been mentioned, that you lose so much energy at the surface. So I had a specific question that actually Xian brought up in one of his early slides, which was about LiDAR, or specifically airborne LiDAR bathymetry. And I'm just curious why the USGS has chosen to put their effort in GPR, not in ALB. And what, more generally speaking, because I don't know much about it actually, what according to the USGS or other people on the panel are the relative benefits and disadvantages of ALB as compared to drone GPR?
So, I try to answer this a little bit in the Q&A text, but maybe folks didn't see it. So I'm not working on LiDAR at all. So there are a couple folks in the USGS who are looking at drone LiDAR under a variety of different conditions. Bathymetry has not been one that has been as successful. So the other issue is that the systems are much more expensive than what we would be looking at for a GPR. And so for us, when you're looking at scale, when we're trying to put them in basically every office across the country, the cost of the sensor is a big consideration. But our hope is that LiDAR will also be, we're not a single silver bullet. So just like I gave the example for the stream velocity, we're looking at Doppler radar, we're looking at particle velocimetry imaging. Though, we're looking at multiple systems, but right now, really the GPR, also for our office, we're a geophysics office. And so we're looking at some of the traditional geophysical methods and how they can be adapted for hydrologic studies and mounted on drones. So yeah, we haven't discounted LiDAR, but we just haven't done a lot of it yet for bathymetry specifically. We don't view it as, we view that the GPR may be more robust, faster.
Okay, thank you.
Remke, I thought I saw another question of yours earlier. Was that answered? I thought it was a different topic. It was on shielding.
Oh, no, it was about the polarization. That was answered, yeah. That was for Jana.
Okay. Did we answer it?
Yeah.
Okay, great. Thank you.
Did you see did the question from Caleb Walter get answered? It's to what extent does the drone's generated EM field increase the signal to noise ratio of a gathered GPR compared to just running the sensor on the ground in traditional setup? I guess it didn't get
For the
answered.
systems we've tested, that hasn't been a significant issue. We thought it would be. We actually thought it would be a significant problem, but turned out it hasn't been. And I think depending on the system, if it were, we would be looking towards solutions similar to what the MAG folks are doing, which is, what kind of sensor aircraft separation do you need to just sort of get outside that noise window? But yeah, happily hasn't been a huge issue for us.
Do you have an IMU on your GPR to measure the noise? I mean, the motion noise from, or the motion of the antenna? And does that impact the data at all?
No. So we operate, so even though we're using off-the-shelf systems, USGS has restrictions on it in terms of the software we can use. And so basically it's for us, for the hexacopter, the GPR doesn't communicate, can't communicate with the aircraft. So we're actually not even, we can't even pull the GPS location tracks from the aircraft. And we used a fixed mount. And so the fixed mount, it was pretty stable. And so we typically had mounted sort of just a quick GPS on the external unit onto the aircraft. So no, in terms of but in theory, the aircraft would have, if it's a fixed mount relative to the aircraft, as long as you have all the GPS information from the aircraft, it's going to talk about sort of any movement in the aircraft itself as well. And you would capture that and be able to correct for it. But also for the bathymetry, for us, it's kind of why it's sort of also a low-hanging fruit in that when we're doing these perpendicular transects across upstream, that water is level. And so basically it's we're looking for that bright reflector of the water surface, and then we're just zeroing that out as level. So for the initial bathymetry data, it's actually less of an issue. But as soon as we get into more complex topography, or if we're moving, in terms of or changes in water level or more complex dry land surveys, that's definitely going to be an issue.
Are there any more questions?
We had one question earlier that I wanted to kind of bring up again and pose to the group. There was a question about, and I think this originally was directed at Jan, the idea of using one drone system with multiple sensors. And so I was hoping that our panelists who've worked with multiple different sensors could maybe address how they've done that, and how difficult or easy it's been to have a single system that has multiple sensor options.
Right. Certainly during the last year in our research project, that was a fundamental point, that if we can come to an industry standardization where a drone would have a standardized coupling system and then standardized power and data requirements, then wouldn't that be great? It would be a modular system where a radar or a mag or a gravimeter or whatever can be placed on a single drone. And that, of course, requires industry manufacturers to agree on a standard, which in geophysics historically has never happened. I mean, the SEG-Y is kind of the best that the industry got to in the 70s. So I'm not sure if that's ever going to get there, but we have the other problem, just physics, right? I mean, how many of these sensors will interfere with each other? So we spoke briefly about UXO detection using MAG and GPR at the same time. That sounds great, and it has been tested, but the problem is that the GPR will create its own magnetic field, and that needs to be muted or somehow ameliorated within the magnetometer. So how many sensors can be combined without cross interference? Certainly if you had radiometrics or some other, a completely different physical phenomena that we're measuring, that's possible. But I think the options there are potentially somewhat limited. Secondly, now we have two sensors to carry from one drone, right? So that's obviously a greater weight limitation as well.
So I think Jan made some very good points, and I do agree with them. And so, but the first one of the first points was actually about the standardization of the connection of different sensors, and this is a kind of a problem that we somehow actually have managed to overcome, in the sense that we have integrated our drone onboard computer with various different sensors, and even though, let's say, the sensors themselves might have different connectors, we have simply already made the cables for this sensor, cables for this sensor, and so on, so that all of them, let's say, can be powered from our onboard computer, which of course takes power from the drone's batteries. And also, it's the computer is made in such a way that it does support different communication protocols, and basically is able to work with different sensors. However, coming back to the point of the drone not being able to carry different sensors, that is indeed the problem. Also because like Jan said, because of the weight of the sensors, this would of course also decrease the flight time of the drone. But I think one solution in cases like this would be to simply have, let's say, if you need to scan one survey area, which you can take the drone with, let's say, on day one, you can use a GPR, you can obtain the data from this location using the GPR, and then on day two, you can take exactly the same drone, flag almost exactly the same mission, but simply use a magnetometer underneath the same drone and then get the magnetometer data. That's probably, I think, currently would be one of the best approaches.
Yeah, that's actually a priority for us right now in terms of, as I mentioned, our vision for the bathymetry is actually a multi-sensor unit. And so I mentioned the snow surveys that we collaborated on earlier this year, and that was actually flew GPR camera for video and photos of the lines at the same time, as well as LiDAR for estimating actual distance of the aircraft or the sensor above the snow surface. So for us, we're really looking at how do we put those together. And one of the challenges, because I fly, our vision is, I fly all sorts of different sensors. And if I could do one flight to, for multiple surveys, that's huge efficiency in the field. But the reality is one of the limitations isn't just the physics of the aircraft and what it can carry, but it also has to do with that the flight parameters for optimized data collection for different sensors are different. So for example, we're talking right now about trying to put the GPR with either the Doppler radar for stream velocity or video for LSPIV, but the heights that those aircraft would have to fly for optimal data collection are completely different. So I can't just do one survey. So, one of the conversations we're having right now, for example, is, okay, does that mean we still want them on the same aircraft? Because there can also be field efficiencies between my just doing one flight where on the same flight, I go out and I do the GPR survey, and then I go up and I do the velocity survey right afterwards without having to bring the aircraft back. And for surveys where differences in timing of data collection from the different sensors matters, even though we're not running those surveys concurrently, anything we can do to sort of decrease the latency between sort of different flights, the lag between different flights can be of value for certain types of data.
Can I just come in here? I think that I would have thought that the prime advantage of a drone is that you can actually have a very high repeatability of your XY location, and then you can adjust your Z for the different sensors with different flights. So picking up on the two comments of Kristaps and Cian, I think that to me is a huge advantage of drone systems, which is only matched by logging systems. When you relog a hole, you can pretty well guarantee that that you're going to be very close in X, Y, Z with your sensor location with different sensors on different runs. But I would have thought that would be the prime advantage of a drone over airborne systems and ground geophysics systems.
I'd say yes and no. So a lot of the surveys I've done in recent years have at the same site, I've run basic photogrammetry, multispectral, and thermal IR surveys at the same sites. And so while the polygon in terms of the outer perimeter of the survey area has been the same, roughly the same, and I can take any of those individual flight plans and fly them as often as I want in terms of temporal changes and hydrologic conditions. The actual transects that we're flying, the flight lines of the individual cameras and sensors vary depending on the camera requirements. So I might, in terms of like the overlap, for example, for different kinds of imagery, my multispectral camera overlap between the different flight lines, and versus the thermal IR are very different because the camera specifications are different. So individual flights are repeatable, but you may not be able to use the same flight plan for different sensors.
Okay.
Yeah, what you say is true. I mean, you have the same problem in marine geophysics. Basically, you have different swath widths of certain sensors and footprints and so forth. Yeah.
All right. Mohammed has his hand up. Mohammed Hajadari. I'm sorry if I mispronounced your last name, but if you'd like to unmute yourself, you can ask your questions directly, and then we'll follow that with a question from Remke Van Dam. I thought I saw a third hand.
Hello, thank you for your exciting speech. I have a question. It's a general question about flying the drones. You know that these drones are not flying on a horizontal level. They have some kinds of roll, pitch, and yaw, and this makes some kinds of noise. And this is not only due to the variations with elevations. Of course, when the drone flies over a terrain or a topography, we expect that it should have some kind of movements like pitch and roll. And I think that your system must somehow record the variations of these kinds of movements. And if we can record them, how we can correct and rectify our data?
All that information is recorded typically by the aircraft itself.
May I comment?
Okay, if you correct it, if you record these movements, how can you, I can say, correct their effects on the data, especially when you are surveying GPR, for example?
We have not needed to for the bathymetry. Our actually flights have been fairly stable and consistent. And also, as I mentioned, we're in a slightly different position than other folks in terms of limitations, and we can't access the GPS, the onboard aircraft GPS for that data at this time. So that's one of the reasons we're looking at external GPS solutions so that we can pull that from something else.
Okay, I'm not talking about GPS itself. I'm talking about some kind of movements, side movements. I mean, pitch, roll, and yaw, for example.
Okay,
do you think that these GPS systems, can we somehow record them? And my question is that you say that we cannot correct these effects at all? We can say that our drone always flies on some stabilized plane always, and I think it is not possible, especially when we have some kind of topography and flies perhaps goes up and down, and then this makes some kind of noise.
I've just answered it based on sort of the bathymetry surveys we're doing. So we have limitations, as I said, that others don't.
Let me comment, colleagues, because we have a lot of experience of flying in very different conditions, situations. So, Mohammed, you are absolutely right. And for example, in waypoints or in turn points, when drone is accelerated or rotates, data from GPR will be almost useless. And effect is more visible for high frequencies of high frequency antennas. So what we can recommend, it's just practical experience. The same as with magnetometers. You should have some overshot for your survey lines outside of your actual survey area. Few meters, you need to add few meters to each survey line. Second, in our recommendations, we limited the maximum wind speed for surveys. For example, if maximum wind speed for DJI 600 drone is around 10 meters per second, we don't recommend to do GPR surveys with wind above 3-5 meters per second. Because if drone is shaky or unstable in the air, you will get a lot of noise and data, and we log all positioning information for the drone: pitch, roll, yaw, speed, altitude. But currently, there is no software on the market which can use that information to remove such kind of noises from the data.
Sorry, what Mohammed was actually talking about is during normal flight, there's still going to be kinematic variations of pitch, roll, and yaw. And he's absolutely right. And if you're talking specifically about GPR, what one must consider, and Jana's slide was really good at this, these are omnidirectional antennas. So if you yaw them to the side 20 degrees, the data is going to look much the same. It's not going to have a significant amount of influence on unshielded antennas. Where the difference will occur is, as Alexei mentioned, is in the high frequency antennas that have some directionality because of the shielding. If you are rolling the antenna, that means it's off nadir and it's off to the side. You will get a slightly lower amplitude. And of course, you're not pointing directly at the ground. And as he said, there's no way currently of correcting for that because it would be hard to predict what the data would have looked like had it been directly downwards. But with unshielded antennas, it wouldn't really be a big difference, and I don't think it would impact the data at all.
Okay. Thank you for your question, Mohammed, and all the great discussion. Remke, if you'd like to please unmute yourself and ask your questions, and then we will follow with Lorraine Godwin.
Unmute. Okay, yeah. I had a quick question. So I have entered the realm of consulting about a year and a half ago, and I see lots of people selling stuff online to clients, people that buy equipment that are not geophysicists, that don't really know what's going on, but they see a buck. So I see lots of outlandish claims personally about penetration depth, about accuracy, about detecting tunnels that are 10 meters or 20 meters below ground and so on, things that cannot be found. I'm actually, first of all, I'd like to ask some of the specialists, including equipment manufacturers like Guideline Geo and software developers like SPH, if they're worried about things like this. And secondly, I'd like to see if there is maybe a role for SEG or another professional organization to sort of develop user guidelines or standards or so on, because I think as a community, we should be very worried about end users getting very quickly unhappy with the product that's being delivered by the community. You know, if you have a few rogue operators, and there are certainly quite a few around already that have bought equipment and that are selling service that they can't actually provide. And I think that as a community, we should be talking about this, and this is a good forum for it, probably.
Can I head that one up? So I work for Guideline Geo with Jana, and I'm actually one of the sales managers for North America. And this is actually an ongoing discussion that we have internally about whether or not we will sell to people who don't have enough knowledge or experience to do what they want to do. So one of the discussions that I have with every potential client is kind of their intentions, in part because certain systems are very customized and you need to know what the purpose of their equipment's going to be to be able to point them to the best system they can use. But also, we really stand behind the idea that our equipment is being used well and correctly. Training is important, and we always disclaim that we do not teach you how to interpret data. We will teach you how to put it into the software. We will teach you how to use and push the buttons on the equipment, but we are not going to teach interpretation, because that is not that is not our wheelhouse as far as what we claim. And whenever I encounter clients who are, well, shall we say, completely incompetent, the discussion comes up about whether or not we are willing to sell equipment to them, because it goes against what we want to see from the industry. We want to really, we want our equipment to show that it can do its job well. And if you have someone who isn't using it correctly talking about it, then that reflects badly on everyone. And the ongoing challenge is between making equipment that's extremely user-friendly, so you can it kind of grow outside of the need for a PhD in geophysics to be competent, but also at the same time acknowledging that that doesn't mean any old person can go and take the equipment and do a good job. So as a manufacturer, we try really hard to balance that. Jana, I don't know if you want to add to that, but that's been my perspective as a member of the sales team for our manufacturer.
Yeah, I totally agree. In Sweden, for instance, when we started to use geophysical investigations in the early 80s, the ones who used the equipment said that, okay, we find anything. Do you want to find a gold treasure? I find it. And that has completely ruined the industry. So we still have people on the railroad road side that doesn't want to use geophysical investigation techniques because they said that we tried that in the 80s, it doesn't work. So we have to be really careful of what we actually say that our instrument can do and use them correctly. I think that geophysics is extraordinary nice, and it's really nice to solve problems. But we also have to be honest and say that these data doesn't give us anything, and go home and drink coffee instead.
And then to add on to that, I wanted to mention, kind of with respect to SEG, Lori and I work together on the near surface technical leadership team, organizing student events. And this month we actually had a student event. It was called Pub Club, and every month we read a paper. And this month's paper was actually a discussion about a variety of different geophysical techniques that have been touted that are not real techniques, that don't work. And that led to a discussion with the students that we work with about the harm that can be done there and the importance of really making accurate claims. So from the SEG perspective, at least in the near surface, we've actually had similar dialogues, in particular with students regarding this exact topic.
I'm just going to jump in there. Remke, hi, Hendit. You know, anybody who's been around the GPR community knows that I'm a bit evangelical about managing expectations, not from a manufacturer's perspective. There's always a certain amount of specmanship on defining how good your radar is or what it can do. That's understandable. And there's a certain amount of ignorance in users, which is always going to be the case, whether it's a guy buying a car and doesn't know how to drive it, or buying an easy locator and think he can find gold treasure. But there's a whole nother category that's been historically endemic within GPR. And those are people who may understand the physics and are just snake oil salesmen. And this has existed since the 1930s. I've put out a lot of papers on the history of GPR scams, essentially, and it goes right back to the original, the first Austrian GPRs that in the Brisbane Courier Mail in 1929, when they reported on the first GPR experiments, said, oh, well, you can find tin deposits with boreholes separated at 30 miles, right? Because people were excited about this, and it goes through history. Remke, you just posted something on LinkedIn yesterday, which is a very good article on airborne GPR. And right away, you can see that discussion could be derailed by questions about how high an antenna could be placed, or what antenna directionality there is, because somebody's got an agenda pointing towards a certain technology that may not have a basis in physics. So GPR specifically in any geophysical technique has been by far, I would say, the subject of bad actors, people who have a technology that believe it works or can oversell it and can find, treasure in the Caribbean, for example, with GPR, literally in the Caribbean Ocean. And there's lots of news articles about that. So that's more of a concern to me, I think, for our industry is actual people trying to scam unaware users.
Yeah, I'd like to, as a user, I'd like to follow up on a lot of what Jans just said. I just completely want to echo it. And it's actually related to the work my office does in hydrogeophysics in general. One of our missions within the USGS is technology transfer and training. So that's not just how to operate the equipment and how to interpret the data, but when should you use it? And we do that with other federal partners as well. And so, we talked just now about the folks running the surveys. We talked about folks who want to learn how to run the surveys, but there's also this other end user who's the environmental site manager, who is making large scale decisions. And so we've been working over years to develop decision support tools to help folks who are not the person who's going to run it, but when somebody's like, GPR can do everything, it's magic, to give them some tools to say, hey, what are the basics that I need to know about this? And are there some basic site parameters that would immediately exclude it? So we're in the process of doing this for groundwater, surface water, interaction, geophysical methods. We have an existing toolbox for fractured rock geophysical surveys, meant for a site manager to say, hey, here's some information about my site. And it'll immediately say, it won't give you all those parameters, but for some sites to say, it's not going to work here. And we envision the same thing for the GPR. And I think that what you're describing is the case for all geophysics. I think a lot of people are like, it's magic, it can do everything. But I think it's extremely compounded by drone fever. So there's this perception that drones are automated from start to finish, that it is, you know, a magic box and you just send it, it does its thing automatically, you're no human involvement, and then it spits out processed data at the end. And you know, the technology though is not quite there. So I think that the perception of drones really makes this even worse, because there are a lot of folks who want to say drones are a huge advocate for it, but it's not a silver bullet.
Let me step in here and sort of make a statement to those that have registered and are participating in this, that we have actually gone over our allotted time. We're now into our networking room. I want to make a quick summary that this has been a wonderful few hours of session. We actually split the Summit of Drone Geophysics over to run over the course of 3 days. So we're technically at the end of this session, and I want to thank all of our presenters and all of those that registered and have been participating, particularly the ones that are participating through asking a lot of really valuable questions for doing so, and for everybody to be here. Technically, we're at the end of our standard event, but and now let me say that tomorrow morning at 10 a.m. Central Time, we'll begin again with day 2, which is on magnetics. I saw that some of the questions that were in the Q&A were kind of about magnetics or related to magnetics, so I'm sure that those questions will be resolved then. Or at least be answered then. I have been, let me address the issue of charlatans in the industry. They've always been here, there will always be here. But it's important for us to inform our customers. And in fact, some of the fundamental reasons for doing this webinar or this workshop is not only to teach ourselves and to share with others that are working in the industry, and share with others who have an interest in it what can be done or what should be done or where the direction of the industry is going in, but it's also to inform our customer base. And I'm going to say in the 70s, I've been around long enough to have spent a few years in this business. I was part of a committee that formed what became the Symposium on the Application of Geophysics to Engineering and Environmental Problems. And the reason that that was an ad hoc committee formed with a bunch of Denver area geophysicists, the reason that came to pass was because there was a lot of bad geophysics being done on EPA projects. And the concept there is if we inform our customers of what's real and what's not real, they can make the decisions that they need to make and what technology they're going to apply and who they're going to hire to actually apply that technology. I think that's probably the best that we can do in our industry, but we need to continually do it. We just can't say, oh, it's done now, we can move on, because there will always be people coming out, and some of it's through their own ignorance or own lack of knowledge, or unwillingness to admit that they can't do something, or their misunderstanding of the technology. Those people will always come to the surface, and we're always going to be battling that problem. The most important thing, though, is that you all are here and you're all talking and actually sharing and recognizing what can be done and with drones, and recognizing some of the issues that have actually bubbled to the surface that those of us been working with drones have recognized and are trying to address. And that's really good. I think that's exactly why we have these kinds of meetings. And in a way, we used to do this when we went to conferences. We're doing it online now through these kind of specialized events. So I want to say thank you to everybody that has participated today. I hope you all will come in tomorrow. Even the presenters that presented today will join tomorrow's event. which will, again, it starts at 10 a.m. Central Time. And on that's on day 2 is on magnetics, and day 3 we're going to go have some presentations on electromagnetics, gamma ray spectrometry, some discussions in QC, QAing data, and then we're going to do a wrap up. At this point, I can't be more pleased than what we've gone through the last several hours. For those who want to leave, you're welcome to do so. For those who want to stay around for the next 45 minutes or so and continue the discussion, we're here, and I look forward to it. So that's really what I wanted to step in and say, hey, we can be done if you can be done if you want to be, but if you want to stick around and talk more about the issues that either technical or legal issues, Jan had mentioned a bunch of the legal issues that impact our industry, the use of drones in our industry. And they're not all about the use of drones. Some of those legal issues, and particularly with GPR, come from other sectors like the FCC. So thank you again. I think we've done a really good job of talking drones this morning. I get accused of just droning on, and I really do need to stop at this point. So
thank you, Ron. I think Lorraine, if you would like to answer or ask your question, please feel free to go ahead and ask your question, and we want to make sure you have that chance.
Sure. Can you hear me? Okay.
Yes.
Yes.
Yes. Okay, great. I just wanted to say to the organizers, great job on organizing this summit. Really topical and interesting speakers today. For those who don't know, Sequent is actually Geosoft. We were acquired 2 years ago by Sequent, and so many of you know us for Oasis Montage software. We are currently planning out a roadmap for the future, and we're very interested in this space. We see a lot of potential in the drone geophysics world, and I just had a question for those who remain on what do you see as the priorities in the drone geophysics world for software, and how could a company like ours keep ahead of the curve, help the all the different instruments that we're seeing come on into this space and the integration of different data types? What would you see as the priorities?
I'm happy to speak to that as an end user of what I really want. I don't want to build my own software. I don't want to have to string together 50 different, Python scripts to get my data in and out and to visualize it. So really what we're looking for, typically for any sensor is a robust flight planning and operations that I can set, once and say, this is for GPR, and then it can automatically pull in all the sort of specs for flight needs for the GPR. And then from the sort of spitting out the other side, to not have to have a geophysicist always involved in some of the data processing. There are cases, obviously, where that's a necessity and it's required, or for a more accurate interpretation, we need that. But for some of our work, we're looking for automated picking that spits out in the field, at least a first order, sort of, for example, for the bathymetry, a cross-sectional area, and spits it out in standard open data formats. So right now we're working for our needs on what those data formats are. And what those numbers would need to look like, what kind of format we actually need. So that's really where we are in terms of I want to be able to integrate. So I want, if folks are raising these questions about motion of the aircraft, and so if there are sensors where that is a factor that needs to be taken into consideration, I want to be able to enter in that sort of flight track information that has that pitch, roll, yaw information as well as the GPS data, and have it automatically handle that. So I also don't want to have to sort of kludge together systems and software that's designed purely for ground coupled. When I have an airborne system with my GPR, like I'm envisioning all these different issues where, for example, my aircraft's kind of going up and down a bit. So even if it's not all level, the ground is, the water surface is changing, the topography is changing. So you have all these different areas of motion change going on. And you need to be able to sort of isolate those different ones in order to interpret the data. And I'd like as much of that handled by the software as possible so that it's built in, that we can account for that. I want everything.
Right, that's great. Thanks. Any other comments out there?
So yeah, I also do agree with the points that Ken made, and I think one of the most important developments that should be made is, I guess we are also kind of moving in maybe in the same direction, at least, you know, like I mentioned in my presentation with the GeoHammer software for GPR data processing. But I think it will be quite important to make the software a bit more user-friendly. It's understandable that, of course, you know, doing data processing and doing it properly, it does take a skilled specialist to do it. But I think there should also be maybe some kind of a bit more simplified way for people to simply, let's say, understand that whether the data that's gathered, whether that data is good, whether it's usable, and maybe even make maybe get some simplified data processing done without the need to have a degree in this. And another thing is that, yeah, of course, in the future of data processing software, what I would like to see is, yeah, I would also like to see more kind of, you know, specific parameters that you can input, that you can, you know, that the software can maybe recognize that, let's say, this survey was done not from the ground, this was done from the drone, and then you can maybe input what this, for example, the speed of the survey, what was the, you know, at what altitude was the drone flying above the terrain, and so all of this can be used to then also adjust the data set.
Just to follow up on that, Ken, there's software out there. There's cloud-based geophysical data software that does bring in the MALA data and can do your automatic horizon picking. It'll do all your crane direction as well as calculate your cross-sectional area. So that's available right now, and that software is bringing in MAG in the next month or two. As well as other sensor technologies. So it's being developed, and the GPR portion is certainly available today.
I think the other big thing for us, and a lot of folks are designing sensors for specific aircraft. And the reality is that the drone field is changing really rapidly. And so I don't want software that's platform specific when it comes to an aircraft. So it needs to be able to work with whatever aircraft, because, you know, the GPR may not change for a couple of years, but, you know, you could go through 3 lifetimes of drone generations in that time period due to rapid advancements or policy changes. So yeah, for me, part of it is also making sure that the software can be used. I can just use it with whatever I want to fly.
All right, I see that Dennis Woods has his hand up. So Dennis, if you'd like to unmute yourself and ask your question, please do so.
I guess this fits into the general discussion we're just having, but my basic question, and I think software might be able to help, is how do we avoid crashing these things? I see that Krista Brass is still with us from Latvia in the middle of the night. And I noticed in one of his slides, he had a 2019 true terrain following implemented. And I wondered if you could expand on that. I mean, just how do we, you know, what software is available? You know, how do we control these things so we can avoid crashing them?
So how to avoid crashing drones? Well, it can be somewhat of a wide topic, you know, but I think the most important thing that we have to put first is operator education. So the drone operator has to be firstly, you know, familiar with the vehicle itself, and has to be familiar with, you know, the software that he's using to control the drone, and also, you know, with all the surroundings. When we're talking about the terrain following, then yeah, we have the system for certain drones, namely DJI M600, DJI M210, and soon for DJI 300. So the way it works is that the system uses a radar or a laser-based altimeter, and it's basically taking measurements multiple times a second in real time, and then the drone is adjusting its altitude based on this. But of course, even with this system, you also need to keep in mind that, you know, there can be other obstacles which this system might maybe not see right away. So then, of course, depending on circumstances where you are flying exactly, you might take certain precautions. So for example, in some cases, maybe if we're not sure whether, let's say, the end of the survey line, maybe it goes too close to some trees, then what we might do, we might maybe use some other drone to simply test whether it corresponds to where, the obstacles are. And if it's safe, then we can use a more expensive drone to fly this. Well, this might seem somewhat of a basic method. It works currently, but of course, what I also see in the future is that drones do have, and some drones already come from the factory with more obstacle detection sensors. So, for example, the DJI M300, for which we will also soon have the support, this will also be able to detect certain obstacles which might be, coming in the way, and also it might stop the drone before the drone will hit the obstacle.
So I guess I also I totally agree with everything that Christoph just said, but I also just want to say to anybody starting out in drone stuff, drones crash. So you need to be prepared for it. You need to expect it, and things happen. So your aircraft can lose adequate GPS data quality. Your batteries can fail, or sudden atmospheric conditions arise. Stuff happens, and so pilot training is really key. And so I get a little bit of a sort of heart palpitations when I read these headlines that are like, we don't want pilot training. And I'm in a bureaucracy, and so every pilot in the whole Department of Interior has had actually the exact same training. So I can operate with anybody. But one of the things that they teach isn't actually how to run a scientific survey. It's what to do when things go bad. And when we talk about our sensors, this is a consideration. So, we have field procedures to try to limit those risks. But when you strap a $50,000, $25,000, or $150,000 tool onto a drone, it's higher risk. And people, especially for me, flying over water, and I've crashed. I know other folks have sunk, fairly expensive systems, and stuff happens. So.
And so I think going back to the topic of risk mitigation, I think one also other important factor is, which I think maybe it would be necessary to also kind of involve some companies from this field, but it's also quite important, especially when you're flying some expensive sensors, expensive cameras, especially over water. It would be important to also think about maybe it's worth getting an insurance in these specific cases. And so that also kind of might maybe bring up the question of how familiar are maybe some insurance companies in certain areas with insuring drones and with insuring expensive sensors. I know they're doing this, of course, in the movie industry when they're using some very expensive, let's say some RED cameras on board drones. So I see something similar, would probably be needed when using sensors. And actually, in many cases, when we have used sensors over water, maybe when we have lent sensors to our customers, then we are also asking that, this drone should have the insurance for the equipment for these days when they're flying.
Dennis, avoiding crashing is a very broad subject for most of us in the drone business. We all want to avoid it, but every time we put an aircraft up in the air, we know there's a risk involved. And we do not have, I have not seen as yet, systems that we can put on these drones. So keep in mind that we're dealing with weight. We have to be very careful we don't load them up with sense and avoid stuff when our true mission is really about doing scientific mapping. It's a challenging topic, I guess, but all of those who have flown drones have crashed drones, and we just learn through experience how put procedures in place, whether it's training pilots, whether it's avoiding flying on certain days because of the weather or whatever. You sort of learn what you can do at this point to diminish the risk. And actually in the US, we really don't want to fly without having some sort of insurance to cover our sensors and our drones. So it is an important topic. I don't want to say anything that might belittle the importance of it, but it's not one that a lot of us are dealing with directly right now, at least in the realm of trying. What we're doing right now is really trying to figure out how best to acquire geophysical data, and that's the whole purpose of this one of the of this event.
You know, Ron, your comments really reminded me sort of the questions I think, you know, that Morgan alluded to earlier, is the role of what role can our professional societies play? And for me, I'm incredibly lucky that I'm part of being this huge bureaucracy, is that even just within the USGS, I have 100 pilots I can pick up the phone and call to be like, hey, have you flown in these atmospheric conditions? Have you flown this kind of sensor? Have you flown this kind of aircraft? And that kind of networking, you know, then I'm not starting from scratch. I'm standing on somebody else's shoulders and building on that learning and finding ways for us to facilitate that sharing within the geophysics community. You know, that's something, especially because I think that there are a lot of challenges, like when we're talking about situational awareness and obstacle avoidance and safety, you know, whether I'm flying a GPR or a MAG or an EM system, I'm flying blind for all of them. So I have these common needs. So I think that any ways we can look at how to harvest that information and share and network is really great.
All right, so any additional questions?
Yeah, just coming back to this question of the roll, pitch and yaw of the drone. Now, some of the suspension systems are flexible and some of them are rigid. How much are we using IMS systems placed, you know, at strategic locations on the actual sensor itself, which may be suspended below the drone? This is quite common in airborne magnetic systems, where the different sensors that are flying below the aircraft also have instruments that measure the orientation of the sensors and so forth. How much is this being employed in the drone sphere, and for what different types of sensors?
So I can answer that. IMS has not historically been, you know, aside for drone applications. I don't know of any systems that incorporate it as yet. And this actually, my answer will lead on to Alfonso, I can't see his last name, who's asking about soil moisture from GPR. So to do that, and this comes back to your IMS actually, I actually have, here's a GPR board, and that's an entire radar system that's very inexpensive to build. The point is that on these radars, there is actually an IMS, because for a certain application, and that is for soil moisture, when you're using radar, there's two ways of doing it. You can use the hyperbolas, but more accurately, you would do a multi-offset. So you'd have one receiver and a series of transmitters, or the other way around, and it becomes a very long sensor. So the sensor itself is about 2 meters long with eight receivers and one transmitter, actually. And to do that properly, we do need to know the directionality of that long sensor. So adding an IMS, yeah, it has been done, and it's very, very easy to do. Those are off-the-shelf products that cost literally a couple $100 for very accurate position and control. So combining that with your RTK gets you a reasonably good idea of your pitch, roll, and yaw on the sensors, as well as positioning. It has been done, but I don't know of any other sensors that do it as yet.
Let's see. Actually, Jan, the MAG Arrow has an internal IMU. GEM Systems builds in one of their magnetometer systems, they include an IMU. There's some EM sensors that have their own IMU. You have to have it, and because you have to know the orientation of the, usually all of these things can include a compass as well. My question about whether or not it's important for GPR was really a question of what are you using it? If it's rigidly mounted to the aircraft, then the IMU of the aircraft should be able to at least give you some idea of what the roll, pitch, and yaw of your antenna is. In the presentations on the next couple of days, there'll probably be some discussion, and Jeff, on the use of IMUs, and certainly for magnetics. It is actually one of the big issues that those in the magnetometry world are starting to deal with.
Just maybe like to follow up on that there. Speaking to the next couple days or whatever, my talk will have some stuff on IMUs and INS systems and how we use that for magnetometry surveys, particularly when we have to suspend the payloads. And this is a big issue and something that we need to correct for in the data. If part of this goes back to the whole quality control and do people know what they're doing, because if you start to break down the data, as I have done with a lot of the magnetic systems, it's a pretty prevalent and large signal in there that needs to be accounted for. So I'm sure this will come up in some of the other talks, more so for magnetics though.
Callum, thank you for that lovely teaser about what's coming up.
No problem.
Yeah, great job, Callum. So.
Well, if there aren't any more questions, then we'll probably begin to wrap up for today. There are 2 more days for those who would like to continue these discussions. We also will share all of the presenters' contact information. It's in both the booklet that you received from Lori, as well as it has been on the screen multiple times, along with Ron's and my contact. And if you want to reach out to Lori or SEG, you can reach them through the near surface email. Outside of that, thank you so much for the discussion. We look forward to continuing this tomorrow with magnetics. And yes, thank you all so much for participating. This has been wonderful.
No, it has. I really want to emphasize that we really appreciate our sponsors, which Lori's been putting on the screen. These companies have been very helpful in allowing us to put this particular presentation, the summit on drone geophysics on. And again, I think I would like to emphasize, if you've got something out of this, if you're in the course of the next year, you want to help the next one, which will be, we're targeting fall of 2021. Please do not hesitate to pitch up and give us some ideas and join the organizing committee. We're all excited about this. This has been a wonderful start today, but we also recognize there's a lot of other voices we want to hear, and there's a lot of other energy we want to get engaged in this whole process. So I thank everyone. I thank Lori and Morgan for being such great people to work with on putting this together today, and all of the presenters and all of the questioners. I hope you join us tomorrow, and as we continue this the workshop summit on drone geophysics.
And sorry, Ron, there was one more thing I wanted to add. We have the desire to really bring together people from this community to allow them a chance to network as much as possible. And while that might be slightly difficult in this virtual format, please take this opportunity to see who has been asking questions that might be relevant to work you're doing, and reach out to them, because these opportunities are the best places to meet collaborators or potential collaborators for the future. I know I saw several different discussions kind of ongoing that seemed to be relevant to each other. So if you need to reach anyone specifically, please reach out to Lori, Ron, and I, and we'll see if they're okay with us sharing contact information, or you can use the chat feature to connect with them directly. If not, we'll continue tomorrow. And once again, thank you to our sponsors, as Laurie is reminding us.
Indeed, thank you. I wish you all a good day or good evening and or good morning, whatever it should be. And we'll see you, we'll reconvene again tomorrow, 10 a.m. Central Time in the, at least US time.
Yeah.
Look forward to it.
Yes, and your connection is good for all 3 days, so don't lose it, and be sure to join us tomorrow.
Yeah, I just as an aside, or just to add what Laurie said, we have set up the registration fee. So if you can't make it tomorrow or Friday, you can log on later and actually participate in viewing the recorded versions of this. So we do appreciate your support and your willingness to participate in this and register for it. And we hope to hear from you. Hope you will join us again tomorrow, and if you're able to. And I think it's been a wonderful start for the Summit on Drone Geophysics.
Yeah, and I should add, clarify that the recording will be available. It will not be available immediately.
Okay.
You will all get an email with the information, but it will be available, just not immediately.
All right.
But shortly.
Yeah. Well, everybody have a great day.